The edge of the solar system. What does that even mean? Is there some invisible wall out there in space marking the point where our sun's reach fades into nothingness? Or is it more of a gradual shift, like stepping from one room into another? These questions aren't just poetic musings. They're the focus of one of the most fascinating mysteries in all of space exploration. At the heart of this enigma lies something called the heliopause, a boundary so distant, so elusive, and so mind-bendingly important that it took humanity decades to even glimpse it. And yet, despite our best efforts, the heliopause remains more mystery than fact. The heliopause isn't just some abstract concept cooked up by scientists. It's a real, physical place in space, where the influence of our sun finally gives way to the vast, uncharted territory of interstellar space. This is the frontier where the solar wind, a stream of charged particles flowing from the sun, collides with the interstellar medium, a thin soup of gas and dust that permeates the galaxy. It's a place where our solar system essentially ends, and the rest of the universe begins. But what exactly happens at this boundary? And how did we even come to know it existed? To understand the heliopause, we first need to talk about the solar wind. Picture the sun as this massive, nuclear-powered generator, constantly blasting out a stream of charged particles in every direction. These particles form the solar wind, which creates a kind of bubble around the solar system known as the heliosphere. Think of it like a protective shield, pushing against the interstellar medium and carving out a region of space dominated by the sun's influence. Now, imagine traveling outward from the sun. As you go farther and farther, the solar wind starts to lose steam. Eventually, it slows down to a crawl, unable to push back against the interstellar medium anymore. That's where you hit the termination shock, a kind of outer edge of the solar wind. But the heliopause lies even farther out, at the very boundary where the solar wind stops altogether and the interstellar medium takes over. For decades, scientists theorized about this boundary but had no way to confirm its existence. That all changed with the Voyager missions. Launched in 1977, the twin Voyager spacecraft were initially tasked with exploring the outer planets, Jupiter, Saturn, Uranus, and Neptune. But their mission didn't end there. Equipped with instruments capable of detecting changes in particle density and magnetic fields, the Voyagers were perfectly suited to go where no spacecraft had gone before, the outermost reaches of the heliosphere and beyond. In 2012, Voyager 1 made history when it crossed the heliopause and entered interstellar space. This wasn't some dramatic, movie-style moment where alarms blared and lights flashed. Instead, the spacecraft quietly reported back data showing a sudden increase in the density of particles around it, evidence that it had left the heliosphere and entered the interstellar medium. Voyager 2 followed suit in 2018, providing even more detailed data about this mysterious boundary. But crossing the heliopause didn't answer all our questions. If anything, it raised even more. For starters, the heliopause isn't a neat, spherical bubble. It's irregular and constantly shifting, shaped by the sun's activity and the motion of our solar system through the galaxy. Some parts of the heliopause are closer to the sun, while others extend farther out. And then there's the question of what lies beyond. The interstellar medium is far from empty. It's filled with cosmic rays, high-energy particles that can pose a serious threat to spacecraft and astronauts. One of the heliosphere's key roles is to act as a shield, deflecting many of these cosmic rays and protecting the planets within. But once you cross the heliopause, you're exposed to the full force of interstellar space. There's also the mystery of how the sun's magnetic field interacts with the magnetic field of the galaxy. The Voyagers have provided some clues, but the data is incomplete. Scientists suspect that the heliopause is a kind of magnetic battleground, where the sun's influence clashes with the interstellar magnetic field. Understanding this interaction could reveal new insights about how stars like our sun interact with their galactic environments. Even the Voyagers themselves are part of the mystery. These spacecraft were never designed to last this long or travel this far. Their instruments are old and limited, and their power supplies are dwindling. Every year, they send back less data, and eventually, they'll fall silent. When that happens, our direct link to the heliopause will be lost, at least until we send new probes to take their place. But why does any of this matter? Why should we care about a distant boundary billions of miles away? The answer lies in what the heliopause represents. It's not just the edge of the solar system, it's a bridge between two worlds. On one side, you have the familiar territory of our sun, planets, and moons. On the other, you have the vast, uncharted expanse of the galaxy. By studying the heliopause, we're not just learning about our own solar system, we're taking our first steps into the wider universe. And there's so much more to discover. Could the heliopause change over time, perhaps growing or shrinking as the sun goes through its cycles of activity? What can it tell us about other stars and their heliospheres? And what mysteries await us in the interstellar medium itself? These are the questions that keep scientists awake at night, and they're the questions that make the heliopause one of the most fascinating frontiers in all of space exploration. But we're just getting started. There's still so much more to unravel about this enigmatic boundary, from its structure and composition to the way it interacts with the galaxy around it. And as we push deeper into interstellar space, who knows what other mysteries we'll uncover? The heliopause, in many ways, represents a living, breathing boundary. It's not static or unchanging but dynamic, constantly shaped by forces both internal and external to our solar system. Imagine trying to map the edge of a balloon as it swells and contracts. It's always shifting. The sun's activity, particularly its solar cycles, plays a critical role in this process. The sun goes through an 11-year cycle of increasing and decreasing activity, marked by the number of sunspots visible on its surface. During periods of high activity, known as solar maximum, the solar wind becomes more intense, pushing the heliopause farther out into interstellar space. Conversely, during solar minimum, when the sun is quieter, the heliopause contracts slightly, allowing the interstellar medium to encroach a bit closer. This fluctuation creates an ever-changing boundary that's anything but predictable. Voyager 1 and Voyager 2, though invaluable, captured only a snapshot of this shifting frontier. Scientists believe that if another spacecraft were to follow in their path a few decades later, it might encounter the heliopause in a completely different location. But the sun's cycles aren't the only factor at play. The heliopause is also influenced by the interstellar medium itself. This medium is not uniform, it's a patchwork of regions with varying densities, temperatures, and magnetic fields. As the solar system moves through the galaxy, it encounters different pockets of interstellar material, which can compress or expand the heliosphere. One of the most intriguing questions is how the heliopause interacts with these interstellar regions. Does it act as a shock absorber, deflecting material around the heliosphere? Or does it absorb some of this material, integrating it into the solar system in subtle ways? These are questions that scientists are only beginning to explore, and the answers could have profound implications for our understanding of both the solar system and the galaxy at large. The Voyagers have already provided some tantalizing hints. For instance, as they crossed the heliopause, they detected a sudden increase in the density of particles, a sign that the interstellar medium is denser than the solar wind-dominated region within the heliosphere. This discovery challenged previous assumptions about the nature of interstellar space, suggesting that it's more dynamic and complex than we once thought. Another surprising finding came from Voyager 1's observations of interstellar plasma waves. Shortly after crossing the heliopause, the spacecraft detected vibrations in the plasma around it. These waves were likely triggered by distant solar eruptions, their energy traveling across the heliopause and into the interstellar medium. This interaction revealed that the boundary between the heliosphere and interstellar space is not a hard barrier but a permeable membrane, allowing energy and particles to pass through in unexpected ways. But for every question the Voyagers answered, they raised 10 more. For example, scientists still don't fully understand the role of the sun's magnetic field at the heliopause. As the solar wind carries the magnetic field outward, it forms a spiral structure known as the Parker spiral. What happens to this magnetic field when it encounters the interstellar medium's magnetic field? Do the two fields merge, creating a complex, tangled region of magnetic turbulence? Or do they remain distinct, each pushing against the other like two opposing forces? Understanding these magnetic interactions is crucial, not just for our knowledge of the heliopause but for our understanding of the galaxy as a whole. Magnetic fields play a key role in shaping the structure and behavior of the interstellar medium, influencing everything from the formation of stars to the propagation of cosmic rays. By studying the heliopause, we can gain insights into these larger processes, using our solar system as a kind of microcosm for the galaxy. One of the most exciting possibilities is that the heliopause could serve as a natural laboratory for studying the interstellar medium up close. The Voyagers have already begun this work, measuring the density, temperature, and magnetic properties of the plasma beyond the heliopause. Future missions could build on this foundation, carrying more advanced instruments to probe the interstellar medium in even greater detail. In fact, there's already a proposal for such a mission, the interstellar probe. This concept, currently under study by NASA, envisions a spacecraft designed specifically to explore the heliopause and the interstellar medium beyond. Equipped with state-of-the-art sensors, the interstellar probe could map the structure of the heliosphere, measure the composition of the interstellar medium, and even search for interstellar dust particles. Such a mission would be a monumental undertaking, requiring decades of travel and cutting-edge technology. But the potential rewards are immense. By venturing beyond the heliopause, we could answer fundamental questions about the nature of our galaxy and our place within it. The heliopause is not just a boundary, it's a bridge, a connection between the familiar world of our solar system and the vast, uncharted expanse of the universe. It's a reminder that even at the edges of what we know, there's always more to discover. And as we push further into the unknown, the heliopause will continue to challenge and inspire us, a testament to the endless curiosity that drives humanity to explore. The heliopause is more than a scientific curiosity. It's a boundary that holds the key to understanding the cosmic environment that our solar system inhabits. One of the most fascinating aspects of this boundary is how it serves as both a shield and a gateway. As a shield, the heliosphere, a bubble carved out by the solar wind, protects our solar system from some of the most harmful cosmic radiation. Beyond the heliopause lies a realm filled with high-energy cosmic rays, originating from events like supernovae and other cataclysmic phenomena in the galaxy. These rays are a constant threat, capable of damaging spacecraft electronics and posing serious risks to human health during deep space exploration. The heliopause acts as the final line of defense, where the solar wind meets and partially deflects these cosmic rays. This protective effect is critical for life on Earth and for the stability of our planetary system. Without the heliosphere, cosmic rays could bombard our planet at much higher levels, potentially altering the atmosphere and affecting biological processes. But the heliopause is also a gateway, offering us a rare glimpse into the vast expanse of interstellar space. By studying the environment just beyond the heliopause, we can gather clues about the composition and behavior of the interstellar medium. This knowledge is crucial for understanding the broader galactic ecosystem and how it influences the formation and evolution of stars and planetary systems. The data from Voyager 1 and Voyager 2 have already revolutionized our understanding of the interstellar medium. For example, scientists were surprised to find that the density of interstellar plasma beyond the heliopause was higher than expected. This discovery has sparked new questions about the nature of the interstellar environment and how it interacts with our solar system. Moreover, the Voyagers detected subtle changes in the magnetic field as they crossed the heliopause. These changes suggest that the boundary is not a simple, static line but a complex, dynamic region influenced by both solar and galactic forces. By analyzing these magnetic interactions, scientists hope to unravel the mysteries of how stars like our Sun interact with their surroundings. One of the most intriguing aspects of the heliopause is its role in the larger context of galactic evolution. The interaction between the heliosphere and the interstellar medium is just one example of a universal phenomenon. Every star in the galaxy creates its own heliosphere, each with a unique shape and size depending on the star's properties and its location in the galaxy. By studying our heliopause, we gain insights into the processes that govern the behavior of stars and their environments on a galactic scale. And yet there's so much we still don't know. For instance, the exact shape of the heliosphere is still a matter of debate. Early models depicted it as a comet-like structure, with a rounded head and a long tail trailing behind. However, more recent data suggests that it might be more spherical, or even distorted by the interstellar magnetic field. Determining the true shape of the heliosphere is critical for understanding how it interacts with the galaxy and how it protects our solar system. Another unanswered question is how the heliosphere changes over time. The Sun's activity varies on an 11-year cycle, but there are also longer-term cycles and fluctuations that could affect the size and shape of the heliosphere. By studying these changes, we can learn more about the history of our solar system and its relationship with the galaxy. The heliopause also holds the potential to reveal new insights about the interstellar medium itself. This mysterious substance, composed of gas, dust, and cosmic rays, plays a critical role in the life cycle of stars and the formation of planetary systems. By studying the properties of the interstellar medium near the heliopause, we can gain a deeper understanding of these fundamental processes. And then there's the question of what lies beyond. The interstellar medium is not uniform. It's a patchwork of regions with different densities, temperatures, and magnetic properties. What will we find as we venture deeper into interstellar space? Could there be regions of space that are denser or more turbulent, and how would they interact with the heliosphere? These questions are not just theoretical. They have practical implications for future space exploration. As humanity begins to plan for missions beyond the solar system, understanding the environment beyond the heliopause will be critical for designing spacecraft that can withstand the challenges of interstellar travel. The Voyager probes have provided us with a tantalizing glimpse of what lies beyond the heliopause, but they are only the beginning. Future missions, such as the proposed interstellar probe, could take us even farther, providing a more detailed picture of this fascinating boundary and the mysteries it holds. The heliopause represents the edge of our solar system, but it also symbolizes the boundless curiosity that drives humanity to explore. It's a reminder that even as we stand at the edge of what we know, there's always more to discover. Beyond the heliopause lies the vast, uncharted territory of the galaxy, filled with wonders we can only begin to imagine. As we continue to push the boundaries of exploration, the heliopause will remain a focus of scientific inquiry, a bridge between the familiar world of our solar system and the unknown expanse of interstellar space. It's a testament to the enduring human spirit, a symbol of our desire to understand the universe and our place within it. The heliopause has also sparked interest because of its implications for cosmic ray research. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from sources such as supernovae, pulsars, and even black holes. These particles carry vital information about the processes occurring in distant corners of the galaxy, but they also pose a danger to astronauts and spacecraft. The heliopause plays a dual role in relation to cosmic rays. It acts as a shield and a filter. Within the heliosphere, the solar wind's magnetic field deflects a significant portion of incoming cosmic rays, reducing their intensity by the time they reach the inner solar system. However, as the Voyagers crossed the heliopause, they detected a sharp increase in cosmic ray intensity, confirming that the interstellar medium is saturated with these high-energy particles. This discovery has profound implications for future missions, especially those that aim to venture beyond the protective bubble of the heliosphere. The environment beyond the heliopause is harsher and more irradiated, requiring advanced shielding technologies to protect spacecraft and their potential human passengers. The data collected by the Voyagers offer crucial insights into the levels of radiation that such missions would encounter and help shape the design of future interstellar explorers. One of the most captivating questions about the heliopause is its role in the galactic ecosystem. Our solar system is not isolated. It's part of a larger cosmic neighborhood, constantly influenced by its surroundings. The heliopause is where these interactions become most apparent. For instance, as the solar system moves through the galaxy, it encounters different regions of the interstellar medium, each with unique properties. Some regions are denser and colder, filled with molecular clouds that may be the birthplace of new stars. Others are hotter and more turbulent, shaped by the shockwaves of ancient supernovae. These varying environments can compress or expand the heliosphere, altering its size and shape. By studying these interactions, scientists can gain a better understanding of how the solar system has evolved over time and how it might continue to change in the future. The heliopause is also a place where the solar wind and the interstellar medium collide, creating a unique region of turbulence and complexity. The interaction between these two forces generates shock waves, magnetic reconnections, and other phenomena that are still poorly understood. These processes may play a crucial role in the transfer of energy and particles between the heliosphere and the interstellar medium, shaping both in subtle but significant ways. To make sense of these interactions, scientists rely on computer models and simulations, informed by the data from the Voyagers. These models attempt to recreate the behavior of the heliopause, taking into account factors such as the sun's activity, the properties of the interstellar medium, and the dynamics of magnetic fields. While these models have made great strides in recent years, they are still far from complete, leaving many questions unanswered. For instance, one of the great mysteries of the heliopause is its asymmetry. When Voyager 1 and Voyager 2 crossed the boundary, they did so at different distances from the Sun, suggesting that the heliosphere is not a perfect sphere but is instead distorted, perhaps by the interstellar magnetic field. This distortion raises intriguing questions about the forces shaping the heliopause and how these forces vary across different regions of the solar system. Another unresolved issue is the nature of the interstellar magnetic field itself. Magnetic fields are notoriously difficult to measure directly, but they play a critical role in shaping the behavior of the interstellar medium and its interactions with the heliosphere. The data from the Voyagers have provided some clues, but much more remains to be learned. One of the most exciting possibilities is that the heliopause could serve as a window into the larger magnetic structure of the galaxy. By studying the magnetic interactions at the boundary, scientists can gain insights into the forces that govern the behavior of the interstellar medium on a galactic scale. This, in turn, could help us understand the processes that shape the formation and evolution of stars, planetary systems, and even galaxies themselves. Looking ahead, the future of heliopause research is filled with promise. The proposed interstellar probe mission, for example, would be equipped with state-of-the-art instruments designed to study the heliosphere and the interstellar medium in unprecedented detail. Such a mission could answer many of the questions raised by the Voyagers while opening up new avenues of inquiry. For instance, the interstellar probe could map the three-dimensional structure of the heliosphere, revealing its true shape and size. It could measure the composition of the interstellar medium, identifying the elements and molecules that make up this enigmatic substance. It could also study the behavior of cosmic rays and magnetic fields beyond the heliopause, providing a more complete picture of the interstellar environment. But even as we look to the future, the legacy of the Voyagers continues to inspire. These twin spacecraft, launched in the late 1970s, have defied all expectations, traveling farther than any human-made objects in history. Their journey to the heliopause and beyond is a testament to human ingenuity and our insatiable curiosity about the universe. The story of the heliopause is far from over. As we continue to explore this boundary and the mysteries it holds, we are reminded of the vastness of the cosmos and the endless possibilities for discovery. The heliopause is not just a line in space, it's a gateway to the unknown, a bridge between our solar system and the infinite expanse beyond. It challenges us to think beyond the familiar, to imagine what lies beyond the edge of our knowledge, and to embrace the adventure of exploration. In doing so, it serves as a powerful reminder of our place in the universe, a small but curious species, reaching out into the cosmos, driven by a desire to understand the world and our place within it. The heliopause is also a dynamic reminder of the interconnected nature of the universe. It's not a static boundary that remains fixed in place. Rather, it is constantly shifting and responding to the interplay of forces from within and outside the solar system. This constant motion is largely influenced by the solar wind, which itself fluctuates based on the sun's activity. During periods of high solar activity, such as the peak of the sun's 11-year solar cycle, the solar wind becomes more intense, pushing the heliopause outward. Conversely, during solar minimums, when the sun's activity wanes, the solar wind weakens, causing the heliopause to contract slightly. This ebb and flow make the heliopause a living, breathing boundary, responsive to the rhythms of the Sun. But the Sun isn't the only force at play. The interstellar medium on the other side of the heliopause also exerts influence, and its properties can vary significantly. Denser regions of interstellar gas can compress the heliosphere, while less dense areas allow it to expand. This interaction is not just a theoretical concept, it's a measurable phenomenon that the Voyager probes have directly observed. For instance, when Voyager 2 crossed the heliopause, it detected a region of increased plasma density in the interstellar medium. This discovery led scientists to speculate that the solar system might be passing through a denser area of the galaxy. Such findings provide a fascinating glimpse into the solar system's journey through the Milky Way, a journey that spans hundreds of millions of years. The idea that our solar system is not stationary but moves through different regions of the galaxy is both humbling and exciting. It underscores the fact that the heliopause is not just a local feature but part of a much larger cosmic framework. As the solar system travels through the galaxy, it encounters varying conditions that can affect not only the heliopause but also the broader environment of the solar system. One of the most intriguing questions about the heliopause is how it interacts with the interstellar magnetic field. Magnetic fields are invisible but incredibly powerful, shaping the behavior of charged particles and influencing the dynamics of the interstellar medium. The data from the Voyager probes have revealed that the interstellar magnetic field is tilted relative to the plane of the solar system, creating a complex interaction at the heliopause. These magnetic interactions are not fully understood, but they could have significant implications for how energy and particles are exchanged between the heliosphere and the interstellar medium. For example, magnetic reconnection, a process where magnetic field lines break and reconnect, might occur at the heliopause, releasing bursts of energy and accelerating particles. Understanding these magnetic processes is crucial for building a complete picture of the heliopause and its role in the galactic ecosystem. It also has practical implications for space exploration, as magnetic fields can affect the behavior of spacecraft and the propagation of radio signals. The Voyager's observations of magnetic fields at the heliopause have already provided valuable insights, but there is still much more to learn. Future missions equipped with advanced magnetometers could map the magnetic structure of the heliopause in greater detail, shedding light on the forces shaping this fascinating boundary. The heliopause is not only a scientific frontier but also a philosophical one. It represents the edge of our solar system, the point where the influence of the Sun gives way to the vastness of interstellar space. Crossing the heliopause is more than a physical journey, it's a symbolic leap into the unknown, a reminder of humanity's unyielding desire to explore. When Voyager 1 crossed the heliopause in 2012, it became the first human-made object to enter interstellar space. This milestone was celebrated around the world as a triumph of human ingenuity and curiosity. It marked the beginning of a new era in space exploration, one where the boundaries of our solar system were no longer the limits of our reach. The crossing of the heliopause by Voyager 2 in 2018 reinforced this achievement and provided additional data that helped refine our understanding of this boundary. Together, these two spacecraft have opened a window into the interstellar medium, offering a glimpse of the universe beyond the Sun's influence. But the story of the heliopause is far from complete. The data collected by the Voyagers have raised as many questions as they have answered, sparking new lines of inquiry and inspiring the next generation of explorers. As we look to the future, missions like the Interstellar Probe hold the promise of taking us even farther, exploring the heliopause and the interstellar medium in unprecedented detail. These missions will not only deepen our understanding of the heliopause but also provide new insights into the nature of the galaxy and the forces that shape it. They will help us answer fundamental questions about the origin and evolution of our solar system, the behavior of interstellar matter, and the dynamics of galactic environments. The heliopause is a boundary, but it's also a bridge between the familiar world of our solar system and the uncharted expanse of the galaxy. It's a place where science meets wonder, where the limits of human knowledge are tested and expanded. As we continue to explore this fascinating boundary, we are reminded of the vastness of the universe and the endless possibilities it holds. The heliopause challenges us to look beyond what we know, to embrace the unknown, and to pursue the adventure of discovery. It's a journey that will take us to the edge of the solar system and beyond, into the heart of the galaxy, and perhaps even to the stars themselves. And it all begins at the heliopause, the edge of the sun's influence, and the gateway to interstellar space. The heliopause, as we've explored so far, is more than a scientific concept. It's a story of exploration, discovery, and our quest to understand our place in the universe. As Voyager 1 and Voyager 2 continue their journeys into interstellar space, their legacy reminds us of humanity's remarkable ability to look outward, even from the confines of a tiny planet in an unimaginably vast cosmos. The data collected by these spacecraft at the heliopause have implications that stretch far beyond this boundary. For example, the interstellar medium itself, the vast expanse of matter that fills the space between stars, is one of the least understood regions in astrophysics. It's composed of a mix of gas, plasma, dust, and cosmic rays, each of which holds clues about the life cycle of stars and the chemical composition of the galaxy. By studying the transition from the solar wind-dominated heliosphere to the interstellar medium, scientists can better understand how the Sun and its bubble interact with the galaxy. The interstellar medium is not homogeneous. It's patchy, turbulent, and constantly in flux. These changes can influence everything from the shape of the heliosphere to the trajectory of cosmic rays. The Voyager's instruments, particularly those capable of detecting plasma density, temperature, and magnetic fields, have helped scientists understand these variations. For instance, when Voyager 1 crossed the heliopause, it detected a sharp increase in plasma density, a signature of the interstellar medium. This finding was groundbreaking, as it provided direct evidence that the spacecraft had left the heliosphere and entered a new region of space. Another key discovery was the realization that the interstellar medium has its own weather, much like the Earth's atmosphere. Shock waves from distant supernovae and other high-energy events ripple through the interstellar medium, creating fluctuations that can propagate all the way to the heliopause. These shock waves can compress the heliosphere, causing it to shrink temporarily, or they can pass through the heliopause, creating disturbances that the Voyagers can detect. This interstellar weather raises fascinating questions about the long-term stability of the heliosphere. Over millions of years, as the solar system moves through different regions of the galaxy, the heliosphere's size and shape likely change dramatically. These changes could have profound implications for the amount of cosmic radiation that reaches the inner solar system, potentially influencing the climate and habitability of Earth and other planets. The asymmetry of the heliosphere is another puzzle that the Voyagers have helped to illuminate. While early models depicted the heliosphere as a spherical bubble, the data suggest it is more akin to a teardrop or comet shape, with a long tail extending behind the solar system. This asymmetry is likely due to the interaction between the solar wind and the interstellar magnetic field, which exerts pressure on the heliosphere, distorting its shape. Interestingly, the distortion of the heliosphere might offer protection to the solar system by deflecting some of the high-energy particles and cosmic rays that would otherwise bombard planets like Earth. This protective role underscores the importance of the heliosphere as a shield, safeguarding life as we know it. Yet, the heliosphere's shield is not impenetrable. Cosmic rays that make it past the heliopause and heliosphere can impact planetary atmospheres and surfaces. On Earth, our atmosphere and magnetic field provide additional layers of protection, but other planets and moons aren't as fortunate. The study of how cosmic rays interact with the heliosphere is crucial for understanding the conditions that might support or inhibit life elsewhere in the solar system. The heliopause is also a fascinating subject for the study of energetic particles. The particles that cross this boundary carry information about the processes that accelerate them, such as shock waves from solar eruptions or interactions with the interstellar medium. Understanding these processes is essential for piecing together the broader puzzle of how energy and matter move through the galaxy. As the Voyagers venture farther into interstellar space, they continue to send back invaluable data, albeit at a slower rate. The power sources on both spacecraft, radioisotope thermoelectric generators, RTGs, are gradually losing their ability to produce energy, and engineers have had to shut down non-essential instruments to conserve power. Despite this, the remaining instruments are still providing a wealth of information about the interstellar medium and its interactions with the heliosphere. These final years of the Voyager missions are bittersweet. On one hand, the spacecraft have already far exceeded their original mission objectives, providing decades of groundbreaking discoveries. On the other hand, their eventual silence will mark the end of an era in space exploration. Even after the Voyagers fall silent, their journey will continue. They are now traveling at such high velocities that they will eventually leave the Milky Way entirely, entering the vast emptiness between galaxies. Each carries a golden record, a time capsule of humanity, filled with sounds, images, and messages intended for any intelligent life that might find them. The inclusion of these golden records highlights another dimension of the heliopause, its philosophical significance. This boundary, where the sun's influence ends, is also a point of connection, a place where the human story intersects with the cosmic story. The golden records serve as a testament to humanity's curiosity, creativity, and desire to reach out to the universe, even across unimaginable distances. As we continue to study the heliopause and the data it provides, we are reminded of the importance of pushing boundaries, both literally and figuratively. The heliopause is not just a scientific frontier, it's a symbol of exploration, a reminder that there is always more to learn, more to discover, and more to understand. In the coming decades, new missions will build on the legacy of the Voyagers, venturing even farther into interstellar space. These missions will carry more advanced instruments, capable of probing the interstellar medium and heliosphere in ways that were unimaginable when the Voyagers were launched. They will explore the outer reaches of the solar system and beyond, answering questions that the Voyagers could only begin to ask. The heliopause, as a boundary, is both a limit and an invitation. It marks the edge of what we know, but it also beckons us to go further, to explore what lies beyond, and to continue the journey of discovery that began when humanity first looked up at the stars. This exploration of the heliopause is a journey not just of science, but of human ingenuity and perseverance. Every step into the unknown, every new discovery, is a testament to our relentless curiosity and drive to understand the cosmos. Even as the Voyagers edge farther into interstellar space, the lessons we've learned about the heliopause fuel our imagination about what lies beyond. One of the most fascinating aspects of the heliopause is its role as a boundary region. While it clearly demarcates where the sun's influence ends, it is not a sharp or fixed line. It fluctuates based on the activity of the sun and the density of the interstellar medium. Solar cycles, which span approximately 11 years, significantly influence the size and shape of the heliosphere. During periods of high solar activity, the solar wind is stronger, pushing the heliopause farther out. Conversely, during solar minimums, the heliosphere contracts, and the heliopause moves closer to the sun. This dynamic nature of the heliopause is more than a theoretical concept, it's a living, breathing boundary. The interplay between the solar wind and the interstellar medium creates a region of constant turbulence. The boundary is not smooth but rippled, with fluctuations caused by interactions between solar wind particles and the magnetic fields of the interstellar medium. These ripples and waves can propagate through the heliopause, creating localized regions of increased or decreased pressure. The turbulence of the heliopause also impacts the behavior of cosmic rays. Cosmic rays are high-energy particles that travel through the galaxy, originating from sources such as supernova explosions and active galactic nuclei. When these particles encounter the heliopause, their trajectories are altered by the magnetic fields and plasma within the region. Some are deflected, while others manage to penetrate the heliosphere and reach the inner solar system. Understanding how the heliopause filters cosmic rays is crucial for multiple reasons, including protecting astronauts on long-duration space missions and studying the potential effects of cosmic radiation on planetary environments. Another intriguing phenomenon at the heliopause is the creation of energetic neutral atoms, ENAs. These atoms are formed when charged particles from the solar wind or the interstellar medium exchange electrons with neutral atoms. Unlike charged particles, ENAs are not affected by magnetic fields, allowing them to travel in straight lines. By detecting these atoms, scientists can create maps of the heliosphere and the heliopause, providing a unique perspective on these regions. Missions such as the Interstellar Boundary Explorer, IBEX, have utilized DNA imaging to study the structure of the heliopause, revealing details that complement the in situ data from the Voyagers. The study of the heliopause also raises questions about the long-term stability of the heliosphere. As the solar system moves through the galaxy, it encounters regions of varying density and magnetic field strength in the interstellar medium. These changes can compress or expand the heliosphere, altering the location of the heliopause. Over geological timescales, these variations could influence the amount of cosmic radiation reaching the inner solar system, potentially affecting the climate and habitability of planets like Earth. For example, if the solar system were to encounter a particularly dense region of the interstellar medium, the heliosphere could shrink significantly, exposing the inner planets to higher levels of cosmic radiation. Conversely, moving into a less dense region could expand the heliosphere, providing greater protection. Studying the heliopause helps scientists understand these potential changes and their implications for the solar system's environment. The exploration of the heliopause also highlights the interconnectedness of space phenomena. The interactions between the solar wind, interstellar medium, cosmic rays, and magnetic fields create a complex and dynamic system. Each component influences the others, shaping the structure and behavior of the heliopause. This interconnectedness underscores the importance of studying the heliopause not in isolation, but as part of a larger cosmic framework. As we look to the future, the legacy of the Voyagers and the heliopause they've explored will continue to inspire new missions. Concepts such as the Interstellar Probe, a proposed spacecraft designed to travel even farther into interstellar space, aim to build on the foundation laid by the Voyagers. These missions will carry advanced instruments capable of studying the interstellar medium, cosmic rays, and the heliopause in unprecedented detail. They will answer questions that the Voyagers could only begin to ask and uncover new mysteries that we cannot yet imagine. The study of the heliopause is also a reminder of the resilience and adaptability of human ingenuity. The Voyagers were launched in the 1970s, with technology that is primitive by today's standards. Yet they have outperformed expectations, surviving harsh conditions and continuing to send back data decades after their launch. Their success is a testament to the vision and skill of the scientists and engineers who designed and built them, as well as the generations of researchers who have analyzed their data. The heliopause, as both a boundary and a bridge, represents the spirit of exploration that drives humanity forward. It is a reminder that even as we probe the farthest reaches of space, we are part of a larger cosmic story, a story that began long before us and will continue long after we are gone. As the Voyagers move deeper into interstellar space, they carry with them a message of hope, curiosity, and the unyielding desire to explore. The heliopause, the edge of the solar system, is not an end but a beginning, a gateway to the vast unknown that lies beyond. In studying this boundary, we not only learn about the universe but also about ourselves, our place in the cosmos and our capacity to dream, discover, and reach for the stars. The heliopause is more than just a physical boundary, it's a dynamic interface that challenges our understanding of the universe. It is a testament to the sun's influence, and a marker of where that influence gives way to the vast expanse of interstellar space. For scientists, it is both a line to cross and a region to study, teeming with phenomena that redefine the limits of our knowledge. One of the most profound realizations about the heliopause is its role in the grand cosmic ecosystem. The interaction between the heliosphere and the interstellar medium is not a one-sided relationship. While the solar wind creates the heliosphere and shapes the heliopause, the interstellar medium also pushes back, influencing the shape, size, and behavior of the heliosphere. This dynamic interaction demonstrates that our solar system is not an isolated island but a part of a much larger, interconnected galaxy. The magnetic fields at the heliopause are a particularly fascinating area of study. These fields, carried by both the solar wind and the interstellar medium, interact in complex ways. The solar wind carries the sun's magnetic field, which spirals outward due to the sun's rotation. In contrast, the interstellar medium has its own magnetic field, which may be oriented differently. At the heliopause, these magnetic fields collide and intertwine, creating regions of turbulence and magnetic reconnection. Magnetic reconnection is a process where magnetic field lines break and reconnect, releasing energy in the form of heat and particle acceleration. Understanding this process at the heliopause can provide insights into similar phenomena observed in other astrophysical environments, such as the magnetic fields of stars and galaxies. The shape of the heliopause is another subject of intense research. Early models depicted it as a roughly spherical shell surrounding the Sun, but more recent studies suggest it may be more elongated, shaped by the flow of the interstellar medium. Some researchers have even proposed that the heliosphere resembles a comet, with a rounded nose and a trailing tail, extending downstream. This shape is influenced by the relative motion of the solar system through the galaxy and the properties of the interstellar medium it encounters. By mapping the shape of the heliopause, scientists can learn about the local galactic environment and how it has changed over time. The heliopause also serves as a natural laboratory for studying plasma physics. Plasma, a state of matter consisting of charged particles, is the primary constituent of both the solar wind and the interstellar medium. The boundary region of the heliopause is a place where different plasmas meet and interact, creating phenomena such as shock waves, turbulence, and particle acceleration. These processes are not only relevant to the heliopause but also to other astrophysical environments, from supernova remnants to the environments around black holes. One of the most intriguing discoveries about the heliopause comes from the study of its outer layer, known as the hydrogen wall. This region, located just beyond the heliopause, is a buildup of neutral hydrogen atoms created by the slowing and compression of interstellar material as it encounters the expanding solar wind. The hydrogen wall was first detected indirectly through observations of ultraviolet light, which is absorbed and scattered by neutral hydrogen. By studying this region, scientists can learn more about the properties of the interstellar medium and how it interacts with the heliosphere. The discovery of the hydrogen wall also raises questions about the boundaries of other star systems. If our Sun's heliosphere has a hydrogen wall, it is likely that other stars have similar structures. By studying these structures around other stars, scientists can compare their heliospheres to our own, gaining insights into the diversity of stellar environments and their impact on planetary systems. The exploration of the heliopause has profound implications for understanding the conditions that influence habitability. The heliosphere acts as a shield, protecting the inner solar system from the majority of galactic cosmic rays. These high-energy particles can have significant effects on planetary atmospheres, climates, and even the potential for life. By studying the heliopause, scientists can better understand how the solar wind and heliosphere have shaped the Earth's environment over billions of years. This knowledge can also inform the search for life on exoplanets, as the presence or absence of a protective heliosphere could significantly impact their habitability. The heliopause is not just a scientific curiosity, it is also a symbol of human exploration. The fact that the Voyager probes have crossed this boundary is a remarkable achievement, representing humanity's first steps into interstellar space. The data they have returned from this region are not just scientific measurements, they are messages from a frontier that we have only begun to explore. The legacy of the Voyager missions is a reminder of the power of human ingenuity and curiosity. Launched with technology that predates modern smartphones, these probes have continued to operate far beyond their expected lifetimes, providing invaluable insights into the heliopause and beyond. Their journey is a testament to the vision of the scientists and engineers who designed them and the generations of researchers who have studied their data. As we look to the future, the exploration of the heliopause and interstellar space will continue to inspire new missions and technologies. The proposed interstellar probe, for example, aims to travel 10 times farther than the Voyagers, carrying advanced instruments to study the heliopause, the interstellar medium, and the broader galactic environment. Such missions will build on the foundation laid by the Voyagers, answering questions we have only begun to ask and uncovering new mysteries that we cannot yet imagine. The heliopause, as a boundary and a gateway, challenges us to think beyond the limits of our current knowledge. It is a reminder that the universe is vast and full of wonders, many of which remain to be discovered. As we continue to study this fascinating region, we not only learn more about the cosmos but also about our place within it. This exploration is not just about crossing boundaries. It is about expanding our horizons and pushing the limits of what we know. The heliopause, the edge of the solar system, is a symbol of that journey, a testament to our unyielding curiosity and drive to explore the unknown. And as we venture farther into the cosmos, it will remain a beacon of discovery, guiding us toward new frontiers and inspiring us to reach for the stars. The heliopause is not merely a line where the sun's influence ends and interstellar space begins. It's a fluid, ever-changing interface. It embodies the complex dance between the sun's solar wind and the interstellar medium, providing valuable insight into how stellar systems interact with their surrounding environments. To grasp the sheer magnitude of its significance, it's worth delving deeper into its role as a boundary and the numerous phenomena that occur within and around it. The sun's influence, primarily through its solar wind, extends outward to create the heliosphere, a protective bubble that shields the planets from a majority of harmful galactic cosmic rays. The heliopause represents the outermost edge of this shield, where the solar wind slows to a stop and is overtaken by the pressure of interstellar particles. This delicate balance between outward and inward pressures creates a dynamic, almost living structure that ebbs and flows with the sun's activity and the conditions in the interstellar medium. One of the most significant aspects of the heliopause is its variability. It's not a static boundary but one that shifts and changes over time. The sun operates on an 11-year solar cycle, during which its activity levels fluctuate. When the sun is more active, the solar wind becomes stronger, pushing the heliopause farther outward. Conversely, during periods of solar minimum, the solar wind weakens, allowing the interstellar medium to compress the heliosphere, drawing the heliopause closer to the sun. These fluctuations provide a unique opportunity to study how the sun's behavior impacts the structure and boundaries of its influence. Voyager 1 and Voyager 2, humanity's emissaries to the interstellar medium, have been instrumental in unraveling the mysteries of the heliopause. Voyager 1, launched in 1977, crossed the heliopause in August 2012, while Voyager 2 followed in November 2018. Despite being separated by over 6 years and significant distances, their crossings revealed valuable information about the heliopause structure and behavior. For instance, Voyager 1 detected an abrupt drop in solar wind particles and a corresponding increase in galactic cosmic rays, signaling its passage into interstellar space. Voyager 2, equipped with additional instruments, provided even more detailed data, including direct measurements of the interstellar plasma's density. One intriguing discovery made by the Voyager probes is the asymmetry of the heliopause. Early models predicted a relatively uniform, spherical shape, but the reality is far more complex. The heliopause is distorted, likely due to the sun's motion through the galaxy and variations in the interstellar medium's pressure and magnetic fields. This asymmetry has significant implications for understanding the sun's interaction with its galactic environment, and provides clues about the forces shaping other stars' heliospheres. Another fascinating aspect of the heliopause is its role as a natural particle accelerator. As the solar wind slows and interacts with the interstellar medium, particles are accelerated to high energies, creating regions of turbulence and shock waves. These processes generate energetic particles that can travel vast distances, contributing to the cosmic ray population observed throughout the galaxy. Understanding how these particles are accelerated at the heliopause can provide insights into similar mechanisms operating in other astrophysical settings, such as supernova remnants and black hole accretion disks. The heliopause also serves as a lens through which we can study the interstellar medium. This region of space, filled with gas, dust, and magnetic fields, is the material from which stars and planets form. By analyzing the interactions at the heliopause, scientists can infer properties of the interstellar medium, such as its density, temperature, and magnetic field strength. This information is crucial for understanding the broader galactic environment and the conditions that influence the evolution of stellar systems. Perhaps one of the most profound implications of the heliopause is its role in protecting life on Earth. The heliosphere, by extension of the heliopause, acts as a shield against a significant portion of galactic cosmic rays, which are high-energy particles originating from outside the solar system. These particles can have detrimental effects on planetary atmospheres and biological organisms, potentially influencing climate and even mutating DNA. The heliopause's ability to deflect or absorb these particles underscores its importance in maintaining Earth's habitability and highlights the delicate balance required for life to thrive. Beyond its scientific significance, the heliopause represents a profound milestone in humanity's exploration of the cosmos. For the first time in history, we have sent spacecraft beyond the protective bubble of the heliosphere and into the vastness of interstellar space. This achievement is not only a testament to our technological prowess but also a symbol of our innate curiosity and desire to explore the unknown. The Voyager probes, with their golden records containing sounds and images from Earth, serve as both scientific instruments and ambassadors, carrying the story of humanity to the stars. As we look to the future, the study of the heliopause and the interstellar medium will continue to be a priority for space exploration. Proposed missions, such as the interstellar probe, aim to build on the legacy of the Voyager spacecraft by venturing even farther into interstellar space. Equipped with advanced instruments, these missions will provide unprecedented insights into the structure of the heliopause, the properties of the interstellar medium, and the Sun's influence on its surroundings. They will also help answer fundamental questions about the nature of the galaxy and our place within it. The heliopause is not just a boundary, it's a bridge to the unknown, a gateway to interstellar space, and a reminder of the interconnectedness of the cosmos. It challenges us to think beyond the confines of our solar system and to consider the broader context in which our world exists. As we continue to study and explore this fascinating region, we are not only expanding our understanding of the universe but also affirming our role as cosmic explorers, driven by a relentless curiosity and an unyielding desire to uncover the secrets of the stars. The mysteries of the heliopause are far from fully unraveled. Each new discovery raises more questions, fueling our desire to probe deeper into this enigmatic frontier. What lies beyond? How does the Sun's influence compare to that of other stars? And what can the heliopause teach us about the broader dynamics of the galaxy? These questions, and many more, ensure that the study of the heliopause will remain a vibrant and essential field of research for generations to come. The heliopause offers a unique glimpse into the balance of forces that govern our solar system and its place in the galaxy. The interstellar medium pressing against the heliosphere is not just a vast void, it's a complex and dynamic environment filled with particles, magnetic fields, and radiation from countless sources throughout the Milky Way. By studying how these forces interact, we are piecing together a broader understanding of how stars, including our Sun, exist within the tapestry of the galaxy. One of the most significant discoveries made by Voyager 1 and Voyager 2 is the detection of the interstellar magnetic field beyond the heliopause. Before their crossings, the precise nature of this field was largely unknown. Scientists theorized that the interstellar magnetic field might be uniform and aligned with the galaxy's plane, but the data from the Voyagers revealed something far more nuanced. The interstellar magnetic field appears to interact with the heliosphere in a complex way, with the boundary itself being influenced and shaped by the pressure and orientation of this field. The heliopause also serves as a laboratory for studying turbulence on an astronomical scale. Turbulence at the boundary results from the interplay of solar wind particles and interstellar particles, creating a chaotic region filled with eddies, shock waves, and magnetic reconnections. This turbulence has implications not only for the behavior of the heliosphere but also for understanding similar processes in other astrophysical contexts. For instance, the same principles of turbulence at the heliopause can be applied to phenomena like the formation of stars, the behavior of accretion disks around black holes, and even the dynamics of galaxy clusters. Another fascinating aspect of the heliopause is how it helps us understand cosmic rays. These high-energy particles originate from outside our solar system, many from distant supernovae, or even more energetic events like gamma-ray bursts. The heliosphere acts as a partial shield, deflecting and slowing some of these particles. However, the interaction at the heliopause creates a unique population of cosmic rays, known as anomalous cosmic rays. These are particles that were originally neutral atoms in the interstellar medium but became ionized within the heliosphere and subsequently accelerated by the solar wind. Studying these anomalous cosmic rays provides critical insights into the processes occurring at the boundary of our solar system and the mechanisms of particle acceleration in space. The asymmetry of the heliopause, revealed by Voyager 1 and Voyager 2, also raises questions about the shape and extent of the heliosphere. Why does the heliopause appear closer to the Sun in one direction compared to another? Scientists believe that this asymmetry may be influenced by several factors, including the motion of the Sun through the galaxy, the density variations in the interstellar medium, and the direction and strength of the interstellar magnetic field. These findings challenge previous models of the heliosphere and underscore the need for further exploration and refinement of our understanding. Additionally, the heliopause is an important reference point for understanding how our solar system compares to others. Every star is surrounded by its own version of a heliosphere, shaped by its solar wind and interactions with the surrounding interstellar medium. By studying our heliopause, we gain a baseline for investigating the boundaries of other stellar systems. This, in turn, helps us understand the environments of exoplanets and the conditions that might make them hospitable to life. The data from Voyager 1 and Voyager 2 has also prompted scientists to rethink the scale of the heliosphere itself. Originally, it was thought that the heliopause marked the definitive boundary of the Sun's influence. However, the discovery of the outer heliosheath, a region beyond the heliopause where solar particles continue to interact with the interstellar medium, suggests that the Sun's reach extends even farther than previously believed. This outer region is still poorly understood, but it represents a new frontier for exploration and study. As we continue to analyze the data from the Voyager spacecraft and plan for future missions, the heliopause remains a symbol of our quest to push the boundaries of knowledge. The challenges of studying such a distant and dynamic region are immense, but they are matched by the rewards of uncovering new insights about the universe and our place within it. The heliopause, as both a scientific frontier and a philosophical boundary, invites us to think beyond the immediate confines of our solar system and to consider the vast interconnected web of forces that shape the cosmos. Even now, decades after their launch, Voyager 1 and Voyager 2 continue to transmit data from the interstellar medium, providing a continuous stream of information about the conditions beyond the heliopause. Their endurance is a testament to human ingenuity and determination, reminding us of the power of exploration and the endless possibilities that await beyond the horizon. As we journey deeper into understanding the heliopause and the vast region beyond, it becomes increasingly clear that the boundary between the Sun's influence and the interstellar medium is not just a point in space but a region of great complexity and dynamic activity. This border is a constantly shifting zone that holds profound implications for our understanding of astrophysical processes, solar dynamics, and the very nature of space itself. The Voyager spacecraft, with their remarkable longevity and mission goals, have given us a glimpse of these complexities, but the full picture is far from complete. While the Voyager probes have crossed the heliopause and provided invaluable data, their journey is far from over. They are now traveling through interstellar space, offering a unique vantage point to study the properties of the space that exists between the stars. This region, once thought to be a void, is actually filled with matter. Though sparse, this matter plays a crucial role in shaping the structure of the galaxy. By studying the conditions in interstellar space, scientists hope to gain insight into the very nature of the galaxy and the processes that govern its evolution. One particularly intriguing aspect of interstellar space is the idea of the local bubble, a large, low-density region of space that our solar system currently occupies. This bubble, thought to have been formed by past supernovae, represents an area of space where the interstellar medium is significantly less dense than in other parts of the galaxy. The heliopause lies at the edge of this bubble, where the solar wind interacts with the surrounding interstellar material. The Voyager spacecraft are helping to map the boundaries of this bubble and understand how its structure influences the movement of cosmic rays and other particles throughout the galaxy. The study of the heliopause and the surrounding interstellar medium also offers valuable lessons in the fields of magnetism and plasma physics. The Sun's magnetic field plays a crucial role in shaping the solar wind and the heliosphere. When Voyager 1 and Voyager 2 crossed the heliopause, they observed a shift in the orientation of the magnetic field, which suggested that the magnetic field of the Sun has a distinct boundary beyond the heliopause. This boundary, known as the magnetic reconnection region, is a place where the Sun's magnetic field lines reconnect with those of the interstellar medium, creating a dynamic zone of energy transfer. The study of this reconnection process is not only important for understanding the solar system's interaction with interstellar space but also provides insights into similar processes that occur around other stars and in other regions of the galaxy. Another fascinating aspect of the heliopause is its role in the solar system's protection against high-energy cosmic radiation. Cosmic rays, which originate from supernovae and other violent events in the galaxy, are composed of charged particles traveling at nearly the speed of light. These particles can pose a threat to both spacecraft and biological organisms. The heliosphere, with the heliopause marking its outermost boundary, serves as a shield that deflects many of these cosmic rays. However, as Voyager 1 and Voyager 2 have shown, not all cosmic rays are blocked, and the interstellar medium itself contributes to the influx of high-energy particles. This makes the heliopause a dynamic and ever-changing barrier that fluctuates in its ability to protect the solar system from harmful radiation. In addition to providing a shield from cosmic rays, the heliosphere also influences the movement of other energetic particles within the solar system. The solar wind, which emanates from the Sun and travels outward, interacts with the planets, asteroids, and other objects in the solar system. The pressure from the solar wind shapes the trajectories of these objects, and even plays a role in the evolution of their atmospheres. Understanding the interaction between the solar wind and the objects within the heliosphere can shed light on the long-term behavior of the solar system and how it has evolved over time. The heliopause also has implications for our search for life beyond Earth. The interstellar medium is filled with molecules and particles that could potentially play a role in the formation of life on other planets. As the Sun's solar wind interacts with this medium, it creates a dynamic environment that could influence the conditions on planets orbiting other stars. By studying the heliopause and the interstellar space beyond, scientists hope to gain a better understanding of how stars and their surrounding environments impact the potential habitability of exoplanets. As we look to the future, the exploration of the heliopause and the regions beyond it will continue to be a focal point of scientific inquiry. New missions, such as the proposed interstellar probe, aim to venture even farther into interstellar space and continue the work that Voyager began. These missions will carry more advanced instruments and technologies, allowing us to gather more precise data about the conditions at the heliopause and beyond. The data collected from these missions will be crucial for understanding not only the boundaries of our solar system but also the broader galactic environment and the forces that shape it. The heliopause, while a boundary, represents much more than the edge of the Sun's influence. It is a bridge to the rest of the galaxy. It connects our solar system to the larger cosmic web and offers a unique perspective on the processes that govern the galaxy. By studying the heliopause, we gain insights into the nature of interstellar space, the behavior of stars, and the complex interactions between cosmic forces. The Voyager spacecraft, and the missions that will follow, continue to push the limits of our knowledge and expand our understanding of the universe. The mysteries of the heliopause and the region beyond are far from solved, but each new discovery brings us one step closer to understanding the vast and intricate cosmos we inhabit. Through the study of the heliopause, we are not only learning about the forces that shape our solar system but also about the broader principles that govern the behavior of the galaxy and the universe as a whole. The heliopause is a reminder that even in the most distant regions of space, there are phenomena and processes that shape the environment in profound ways. The journey to understand the heliopause and its place in the cosmos is an ongoing one, and each discovery brings us closer to unraveling the mysteries of space. As the Voyager probes continue their journey into the unknown, they serve as beacons of human curiosity and exploration, symbolizing our relentless drive to understand the universe and our place within it. The heliopause may mark the edge of the solar system, but it also marks the beginning of a new era of discovery, one that promises to reveal the true nature of the cosmos and the forces that govern it. As we venture farther into the mysteries of the heliopause, we begin to realize that this boundary is not simply an edge, but a window into understanding the complex interplay of forces that govern not only our solar system but the larger universe. The Voyager spacecraft, having crossed the heliopause, are providing unprecedented data that will likely influence astrophysical research for decades to come. Each passing day, as these spacecraft move deeper into interstellar space, they offer insights that scientists could only dream of before. Their journey is a testament to human ingenuity, pushing the limits of exploration and technology in ways that continue to captivate the imagination. While the heliopause serves as a boundary between the Sun's influence and the interstellar medium, it's also a dynamic frontier where the laws of physics are put to the test in ways that can't easily be replicated in laboratories on Earth. The extremely low-density region that surrounds the solar system is filled with particles that move at high velocities, but it's also a place where the Sun's magnetic field and the interstellar magnetic field meet and interact in fascinating ways. As the Voyager probes travel farther, they provide data on how these magnetic fields influence the dynamics of this region, offering new insights into the behavior of the solar wind and the forces at play in the larger interstellar medium. The magnetic fields at the heliopause also play a significant role in shaping cosmic rays, which are high-energy particles that travel through space. These particles, originating from sources such as supernovae, black holes, and other high-energy events, are a key element in understanding the processes that govern the behavior of matter in space. By studying how the heliosphere interacts with these particles, scientists can gain a better understanding of the effects cosmic rays might have on life, technology, and the future of space exploration. The heliosphere acts as a protective shield, filtering out some of these rays, but the forces at play within the heliopause still allow some to pass through, contributing to the cosmic rays that reach us here on Earth. Beyond cosmic rays, the heliopause also offers clues to the formation and evolution of stars and planetary systems. Understanding how solar wind interacts with the interstellar medium at the edge of the solar system can help astronomers gain insight into similar processes that occur in other parts of the galaxy. This could eventually lead to a deeper understanding of star formation, the behavior of planetary atmospheres, and the conditions that make certain regions of space more conducive to the formation of life. The boundary where our solar system ends and interstellar space begins is a pivotal zone for comprehending the mechanisms that shape stellar evolution and the potential for life beyond our solar system. The heliopause is also a crucial point of study for future space exploration. As humanity looks to send missions farther into the depths of space, understanding the environment beyond the heliosphere will become increasingly important. The interstellar medium is vastly different from the conditions we encounter within the solar system. Solar winds, cosmic radiation, and magnetic fields behave differently, and spacecraft venturing into these regions will need to account for the challenges posed by these unique conditions. The Voyagers, as they move into uncharted territory, serve as a precursor to future missions, offering a first-hand look at the difficulties and opportunities of interstellar travel. Moreover, the journey of the Voyager probes is laying the groundwork for understanding how we might one day send humans on a similar journey. The data gathered by Voyager 1 and Voyager 2 will inform future technologies designed to withstand the harsh conditions of deep space. From radiation shielding to propulsion systems, the lessons learned from these spacecraft will shape the design of future interstellar probes and, potentially, manned missions to distant stars. The heliopause represents a point where humanity will have to push the boundaries of space travel and technology, overcoming challenges that were once thought insurmountable. As the Voyager probes continue their journey, they are also becoming ambassadors of humanity's reach into the unknown. These spacecraft carry with them the golden record, a message to any intelligent life that may one day encounter them. This symbolic gesture reflects the hope that, even in the vastness of space, the human story can travel beyond the confines of our solar system and connect with beings from other worlds. In this way, the heliopause is not just a scientific boundary but a philosophical one, representing humanity's desire to explore, understand, and communicate across the stars. Looking ahead, the future of heliopause exploration is filled with promise. While the Voyagers are aging and their power sources are dwindling, new missions are on the horizon that will continue the work they began. These future missions will build upon the discoveries made by Voyager 1 and Voyager 2, using more advanced instruments and technologies to probe the mysteries of the heliopause and beyond. In particular, the proposed interstellar probe mission is designed to journey beyond the heliopause and explore the interstellar medium in greater detail. This mission aims to study the properties of interstellar space in ways that the Voyagers could not, offering even more detailed insights into the structure and dynamics of the space beyond our solar system. The heliopause will continue to be a key area of interest as we search for answers to some of the most profound questions about the universe. How does the Sun influence the interstellar medium? What are the implications of the heliopause for cosmic ray research? How do the boundaries of the solar system shape the behavior of the galaxy? These are just a few of the questions that will drive research in the coming decades. The study of the heliopause is part of a larger scientific endeavor to understand the forces that govern the cosmos, and with each new discovery, we are one step closer to unlocking the mysteries of the universe. As we continue to explore, the heliopause will remain a symbol of the boundaries we have crossed and those yet to be crossed. It marks the edge of the solar system, but it also marks the beginning of our journey into the broader cosmos. The Voyager probes, with their remarkable discoveries, have opened the door to a new era of space exploration. The heliopause is no longer a distant and mysterious boundary. It is a frontier that we are learning to understand, and as we peer beyond it, we gain a deeper appreciation for the vastness and complexity of the universe. The journey of discovery continues, and with it, the hope that we will one day understand our place in the cosmos. As the Voyager probes continue their journey through the void, the legacy they leave behind grows ever more profound. The heliopause is not just an abstract scientific concept, or a mere boundary marking the end of our solar system. It is the doorway through which humanity has begun to venture into interstellar space. While we still have much to learn about this vast region, the data collected by these probes is already offering a wealth of knowledge that continues to challenge and inspire scientists across the globe. One of the most intriguing aspects of the heliopause is how it can help us better understand the nature of stars and planetary systems. When we study the interaction between the solar wind and the interstellar medium at the edge of the solar system, we are also investigating fundamental processes that likely occur in other star systems throughout the galaxy. The interactions that take place at the heliopause can provide insights into how stellar winds shape the environments of planets, and how these environments, in turn, affect the development of life. While Earth is the only known planet that harbors life, there is a growing recognition that the factors influencing habitability might not be unique to our system. In fact, understanding how our Sun's solar wind interacts with the interstellar medium could offer clues about how other stars might influence the habitability of their own planets. The heliopause may also be crucial for understanding the larger structure of the Milky Way galaxy. The Sun, like all stars, resides in the midst of an interstellar medium that is made up of gas, dust, and energetic particles. The heliopause represents a physical boundary where the pressure from the solar wind meets the forces from the surrounding galactic environment. By studying the heliopause and the transition zone between the solar wind and the interstellar medium, scientists can learn more about the distribution and composition of matter in the galaxy. This knowledge could help to refine our models of galactic formation and evolution, shedding light on the fundamental processes that shape the structure of the Milky Way and other galaxies. Furthermore, the study of the heliopause can contribute to our understanding of cosmic magnetism. Magnetic fields play a crucial role in the behavior of the interstellar medium and the dynamics of plasma and space. The interaction between the solar wind's magnetic field and the interstellar magnetic field is a key area of research, and the heliopause serves as a natural laboratory for studying these phenomena. Understanding how these magnetic fields interact with one another could have broader implications for our knowledge of astrophysical processes across the universe. For example, it could provide insights into the behavior of cosmic jets produced by black holes, the formation of stars, and the large-scale structure of the universe itself. In addition to the scientific value of studying the heliopause, the exploration of this boundary also raises important philosophical questions. The idea that we are capable of sending spacecraft beyond the confines of our solar system forces us to rethink our place in the universe. For centuries, humanity viewed the Earth as the center of everything, but as our understanding of the cosmos has evolved, we have come to realize that we are but one small part of a vast and interconnected universe. The heliopause represents the edge of the solar system, but beyond it lies a much larger, unknown expanse that we are just beginning to explore. As we venture farther into this uncharted territory, the heliopause serves as a reminder of the vastness of the cosmos and the limits of human knowledge. It challenges us to think about the future of our species and the potential for life beyond our planet. The idea of reaching beyond our solar system has long been a dream of science fiction, but the data returned by the Voyager probes shows that it is not merely a fantasy. We are slowly but surely extending our reach into the cosmos, and the heliopause is just the first step. While we have yet to fully understand the implications of crossing this boundary, we can be certain that the knowledge we gain will shape the future of space exploration. As we learn more about the interstellar medium, cosmic rays, and the forces that shape our galaxy, we are not just unlocking the secrets of the universe, we are also preparing for the future of space travel. One of the next major steps in our exploration of the heliopause and beyond will be the development of more advanced spacecraft capable of traveling farther into interstellar space. The Voyager probes, while groundbreaking, are limited by their aging technology and power sources. As they continue to drift away from the Sun, they are gradually losing the ability to communicate with Earth, and their missions will eventually come to an end. However, the lessons learned from the Voyager missions will inform the design of future spacecraft, such as the proposed interstellar probe mission, which aims to study the interstellar medium in greater detail. The interstellar probe mission is one of several proposed missions that would take advantage of the knowledge gathered by the Voyager spacecraft to push even farther into space. This mission is designed to travel beyond the heliopause and explore the regions of space that lie in the interstellar medium. Equipped with more advanced technology, including instruments capable of detecting the subtle properties of interstellar gas and magnetic fields, the interstellar probe will build on the work of Voyager 1 and Voyager 2. It will provide us with an even deeper understanding of the solar system's boundary and the forces that govern the space between stars. While the future of heliopause exploration is exciting, it also presents numerous challenges. The vast distances involved, the hostile environment of interstellar space, and the limitations of current technology all pose significant obstacles to further exploration. However, the continued development of space technology, such as advanced propulsion systems and radiation shielding, will eventually make it possible to send spacecraft much farther into the cosmos. Perhaps one day, we will send human missions beyond the heliopause, opening up the possibility of interstellar travel. The exploration of the heliopause and the region beyond it is a testament to the incredible achievements of human space exploration. The Voyager probes have already made history by becoming the first human-made objects to enter interstellar space, and their journey continues to inspire generations of scientists, engineers, and explorers. As we push the boundaries of space exploration, the heliopause will remain a key point of focus, offering insights into the forces that shape our solar system, the galaxy, and the universe as a whole. The heliopause represents more than just a physical boundary. It symbolizes the spirit of exploration that drives humanity to reach for the stars, to venture beyond the known and into the unknown. The mysteries of the heliopause and the interstellar medium will continue to captivate scientists for years to come, as they unravel the secrets of this distant frontier. And as we continue to study the heliopause, we will gain a deeper understanding of the cosmos, our place within it, and the possibilities that lie ahead. As the Voyager probes continue their journey into the vastness of interstellar space, they provide an unparalleled opportunity for scientists to study the interactions between our solar system and the surrounding environment. While Voyager 1 and Voyager 2 have already crossed the threshold into interstellar space, there is still so much to learn about the nature of the heliopause and its role in shaping the conditions beyond our solar system. The data collected by these probes is invaluable, and as the probes move farther from the Sun, they continue to offer new insights into the nature of space, the solar wind, and the interstellar medium. One of the most intriguing aspects of the heliopause is how it influences the cosmic rays that bombard our solar system. These high-energy particles, which originate from outside our solar system, are constantly streaming through space, and their behavior is influenced by the solar wind and the magnetic fields that extend beyond the Sun. At the heliopause, these cosmic rays experience a dramatic shift in their behavior. The solar wind's pressure diminishes, and the interstellar medium takes over. This transition is thought to create a region where the cosmic rays experience a change in their energy levels and their path through space. By studying this boundary and the interactions that take place there, scientists are gaining a better understanding of the fundamental forces that govern the behavior of cosmic rays. These particles are not only important for our understanding of space weather but also for understanding the processes that occur in the broader universe. Cosmic rays play a significant role in the formation of stars, the behavior of galaxies, and even the development of life on Earth. By learning how they interact with the solar wind and the interstellar medium, we can gain a deeper understanding of the processes that shape the universe around us. The heliopause also offers a unique opportunity to study the properties of the interstellar medium. This is the matter that exists between stars in a galaxy, composed of gas, dust, and energetic particles. While much is known about the interstellar medium within our galaxy, the data from the Voyager probes is providing new insights into its composition and behavior. For example, scientists have been able to measure the density of the interstellar gas in the region surrounding our solar system, revealing important information about the overall structure of the Milky Way. One of the key questions that scientists are trying to answer is how the heliopause interacts with the interstellar medium in different regions of the galaxy. The solar system is not isolated. It is part of a much larger galactic ecosystem. Understanding the structure and behavior of the interstellar medium is essential for understanding the larger-scale dynamics of the galaxy. The data from the Voyager probes is helping to shed light on the nature of the interstellar medium in the local neighborhood of the Sun, and how it may differ from other regions of the galaxy. Another fascinating aspect of the heliopause is the role it plays in the larger-scale dynamics of the galaxy. Our Sun is just one of billions of stars that make up the Milky Way galaxy. The heliopause represents the boundary where the solar wind's influence begins to fade and the forces of the interstellar medium take over. This boundary is not static. It is constantly shifting and changing as the Sun moves through different regions of the galaxy. The behavior of the heliopause could provide valuable insights into the larger-scale structure of the galaxy and the forces that govern the motion of stars and the behavior of interstellar matter. As the Voyager probes continue their journey, they are also providing data that could be used to improve our understanding of the broader universe. The study of the heliopause and the interactions between the solar wind and the interstellar medium is an important step toward understanding the nature of space beyond our solar system. The data from these missions will contribute to our knowledge of the fundamental processes that govern the behavior of matter and energy in the universe. One of the key challenges in studying the heliopause is the vast distances involved. Even with the incredible speed of the Voyager probes, it will take them tens of thousands of years to travel far enough to reach the outer reaches of interstellar space. However, the data they are sending back is providing invaluable information that will continue to inform scientific research for generations to come. The study of the heliopause and the surrounding region is not a short-term project. It is a long-term endeavor that will continue to yield new discoveries for many years. In the future, new spacecraft will be able to build on the work done by the Voyager probes and explore the heliopause and the regions beyond it in even greater detail. For example, the proposed interstellar probe mission, which aims to travel beyond the heliopause, will carry advanced instruments designed to study the interstellar medium in unprecedented detail. This mission, which is still in the planning stages, will follow in the footsteps of the Voyager probes, but it will be capable of gathering more detailed data about the environment beyond the solar system. As we continue to explore the heliopause and the region beyond, we are also learning more about the fundamental forces that govern the universe. The interaction between the solar wind, the heliopause, and the interstellar medium is a complex and dynamic process that shapes the environment of our solar system and the broader galaxy. The study of this region is helping scientists to unravel some of the most profound mysteries of space, from the behavior of cosmic rays to the structure of the Milky Way. But the heliopause is not just a scientific curiosity. It is a symbol of human achievement and our quest for knowledge. The fact that we have sent spacecraft to the edge of our solar system is a testament to the incredible progress humanity has made in space exploration. The Voyager probes have already achieved remarkable feats, and their continued journey into interstellar space is a reminder of our potential to push the boundaries of exploration and discovery. As we continue to explore the heliopause and the region beyond, we are not just gathering data for the sake of scientific advancement. We are expanding our understanding of the cosmos and our place within it. The mysteries of the heliopause and the interstellar medium are not just questions for scientists to answer. They are questions for all of us to ponder as we contemplate the vastness of space and our future in it. The study of the heliopause offers us a glimpse into a future where humanity may one day venture beyond the confines of our solar system. While we are still a long way from sending humans into interstellar space, the knowledge we are gaining from the Voyager probes and future missions will lay the groundwork for future generations to explore the stars. As we continue to push the boundaries of space exploration, the heliopause will remain a critical area of study, helping to unlock the mysteries of the universe and guiding us toward new frontiers in space. The exploration of the heliopause also speaks to the evolution of human curiosity and innovation. For centuries, humans have looked up at the stars, wondering what lies beyond the limits of our understanding. The heliopause is a tangible representation of that frontier, a boundary that once seemed insurmountable, now within reach thanks to the advancements in technology and space exploration. The fact that we've sent spacecraft to explore the edge of the solar system is not just an achievement in engineering but a leap for humanity itself. It symbolizes the growing ambition of space exploration, the drive to understand the cosmos, and the quest to answer some of the most profound questions of existence. In addition to the scientific and philosophical significance, the heliopause represents a natural threshold between two vast and incomprehensible regions, the Sun's influence and the uncharted territory of interstellar space. This boundary acts like a cosmic curtain, marking the transition between two distinct environments with different physical properties. Just beyond it, there is a noticeable change in the solar wind's behavior. Cosmic rays become more intense, and the pressure exerted by the Sun's magnetic field becomes negligible. This dynamic shift is a crucial aspect of understanding not only our solar system but the interaction between solar systems and the broader galaxy. The study of the heliopause will, therefore, be essential in any future mission to explore the greater depths of interstellar space. The Voyager probes are invaluable, not just for the current data they continue to send back but also for the legacy they leave behind. They are, in essence, ambassadors of Earth. As they journey farther into interstellar space, they carry with them golden records containing sounds and images meant to represent the diversity of life on Earth, a hopeful message for any intelligent beings that might one day encounter them. This golden record, while a symbolic gesture, reinforces humanity's deep desire to reach out into the cosmos. Voyager 1, having crossed into interstellar space, now carries this record farther than any human-made object, setting a precedent for future space missions that will seek to understand even more about our universe. With each new piece of data from Voyager 1 and 2, scientists are continuously refining their understanding of the heliopause. For instance, the difference in particle density between the solar wind and the interstellar medium has provided new insights into the mechanics of plasma physics. The way these two environments interact at the boundary is not just a curiosity. It has direct implications for how interstellar dust and magnetic fields operate. These insights are crucial for future interstellar probes that will have to navigate these unknowns in order to gather accurate data as they travel further out into space. Understanding the heliopause also helps us better understand our solar system's journey through the galaxy. The Sun, along with its planets, is constantly moving through the Milky Way, and this motion influences the heliopause position. The solar system travels at an average speed of about 828,000 kilometers per hour, 514,000 miles per hour, as it orbits the galactic center. This motion causes the boundary of the heliopause to shift over time, and understanding this shifting helps scientists model how our solar system interacts with the galaxy's cosmic environment. This is a relatively slow process, but it has implications for the Sun's interaction with nearby stars and cosmic phenomena, influencing the conditions that might affect us in the future. There are also questions surrounding the potential for new discoveries beyond the heliopause. We've only just begun to explore the nature of interstellar space, and while the data from Voyager gives us valuable insight, there is so much more to uncover. What other phenomena exist in this uncharted space? Is there a way to measure the interstellar medium's full composition in more detail? How will the solar system's movement through the galaxy continue to affect the heliopause size and behavior? These are just a few of the questions that future missions will need to address as we extend our reach further into the unknown. One particularly exciting aspect of the future is the possibility of humanity one day venturing into interstellar space itself. Although such a mission is still far off, the groundwork laid by the Voyager probes and similar future missions could set the stage for human space travel beyond our solar system. Proposals for new spacecraft like the Breakthrough Starshot initiative are already in motion, aiming to send small, fast probes to nearby star systems within decades. These projects are an ambitious step toward human exploration of the stars and could someday complement the knowledge we gain from studying the heliopause. Another area where the heliopause plays a significant role is in protecting Earth from harmful cosmic rays. The solar wind and the magnetic fields that extend far beyond the planets serve as a protective shield for the Earth, deflecting high-energy particles from distant stars and supernovae. The boundary at the heliopause is the region where this protective effect begins to diminish, and beyond it, interstellar radiation becomes more prominent. Understanding how the solar wind interacts with the surrounding space environment can help us better comprehend the long-term effects of cosmic rays on the solar system and our planet. This research may also help future astronauts who venture beyond Earth's protective bubble into deep space, where radiation is far more dangerous. The study of the heliopause also opens the door to broader discussions about the future of space exploration. As humanity continues to push the boundaries of space exploration, the heliopause will likely become a key point of interest for new missions that will aim to explore the outer edges of the solar system and beyond. With technological advances like ion propulsion systems and powerful telescopes, we could one day send probes further into interstellar space, unraveling the mysteries of the heliopause and the interstellar medium in more detail than ever before. In the meantime, the Voyager missions will continue their solitary journey, sending back data that will be analyzed for decades. These spacecraft will likely remain the only representatives of human curiosity in interstellar space for many years to come, but the legacy they leave behind will continue to inspire generations of scientists, explorers, and dreamers. The heliopause, in all its enigmatic wonder, serves as a reminder of how much we've learned and how much there is still to discover. The boundary between the solar wind and the interstellar medium is not just an academic concept. It's a fascinating frontier that holds the answers to questions about our place in the universe and the forces that govern it. As we move forward in our quest for knowledge, we must look to the heliopause not only as a milestone in space exploration but as a symbol of our endless curiosity and our drive to explore the unknown. The study of the heliopause and its surrounding space holds immense value, not only for our understanding of the solar system but for our broader understanding of the universe. The Voyager probes have offered us a glimpse into a part of space that was once beyond our reach, and their discoveries have opened the door to future explorations that could unlock even more mysteries. The heliopause is not just a boundary, it is a gateway, a symbol of our quest to push further into the unknown, and a testament to the boundless curiosity that drives humanity to explore the cosmos. As we look to the future, the study of the heliopause will continue to play a pivotal role in shaping our understanding of space and our place within it. As we continue to expand our exploration of the heliopause and interstellar space, the scientific community remains captivated by the mysteries that lie beyond our solar system. The heliopause itself, which marks the outermost boundary of the solar wind's influence, represents more than just a physical location. It embodies humanity's aspiration to go beyond the familiar and step into the unknown. And while the Voyagers continue their silent journey far beyond where human eyes can see, each new piece of data sent back helps us reframe our understanding of space itself, revealing truths that challenge previous assumptions. For one, the behavior of the heliopause suggests that the solar wind is not a simple, uniform force. Scientists have discovered that the boundary is actually shaped by the varying pressures and magnetic fields exerted by both the Sun and the interstellar medium. This dynamic nature of the heliopause suggests that it is not a static wall but a constantly fluctuating region, where the force of the Sun's solar wind collides with the interstellar environment, creating turbulent waves of particles and energy. This turbulent interaction, although subtle, plays a significant role in how the solar system interacts with the broader galaxy, offering clues about the energy flow between stars and the influence of cosmic phenomena on planetary systems. Interestingly, the heliopause also provides a key window into understanding the broader workings of the Milky Way. The interstellar medium, composed of gas, dust, and cosmic rays, extends throughout the galaxy, and its influence on the solar system can only be truly understood by studying the region surrounding the heliopause. By monitoring how the solar wind interacts with this medium, scientists are able to map out the properties of interstellar space, improving our knowledge of the conditions in which stars like our Sun are born, live, and eventually die. This interaction is also crucial in understanding the phenomenon of cosmic rays, high-energy particles that originate from distant supernovae and other cosmic events. These particles pose a potential hazard to future interstellar travelers, making the heliopause an essential boundary for studying the radiation that exists beyond the protective shield of the Sun. The data transmitted by the Voyager probes have revealed that beyond the heliopause, cosmic rays from other star systems become much more prominent. These cosmic rays, which can potentially damage living tissues and electronic equipment, represent one of the greatest challenges for interstellar travel. The heliopause, in a sense, provides a shield, albeit a weakened one, as it deflects a significant portion of these high-energy particles. But as humanity looks ahead to interstellar exploration, understanding the full nature of the radiation beyond the heliopause becomes increasingly critical. This will require new technologies to protect astronauts from the dangers posed by cosmic radiation, ensuring that any future missions beyond our solar system are as safe and feasible as possible. Looking at the Voyager's achievements from a historical perspective, they represent a monumental leap in human ambition. When the probes were first launched in 1977, the notion of sending a spacecraft to the edge of the solar system seemed almost impossibly far-fetched. The technology of the time was far less advanced than what we have today, and the challenges of interstellar space were not as well understood. Yet, through a combination of ingenuity, perseverance, and time, Voyager 1 and 2 have continued their journey, overcoming countless obstacles and unforeseen challenges. Their success is a testament to the resilience of scientific endeavor and the determination to push the boundaries of knowledge. In the years since the Voyagers were launched, advances in technology and space exploration have continued at a rapid pace. With the development of more advanced spacecraft, faster propulsion systems, and cutting-edge scientific instruments, we are now better equipped than ever to explore the unknown regions beyond the heliopause. New space missions, such as the Parker Solar Probe, are actively studying the Sun itself and its influence on the solar system. These probes are helping scientists refine their understanding of how solar winds interact with planetary atmospheres, how the heliopause forms, and how the entire solar system moves through the galaxy. As these missions continue, they provide the necessary building blocks for understanding the bigger picture of space exploration. One key development that could redefine our approach to space exploration is the potential for utilizing interstellar propulsion technologies. Current space missions, such as those conducted by NASA and private companies, rely on chemical rockets that provide limited speed and efficiency. However, breakthroughs in areas like ion propulsion, nuclear fusion, and even theoretical concepts such as the Alcubierre drive could revolutionize the way we travel through space. The heliopause, as a distant boundary that we have only just begun to study, could become the target of future spacecraft that employ these new technologies. By understanding the behavior of the heliopause and its surrounding space, scientists could determine the best ways to navigate and explore regions far beyond our solar system. Interstellar travel, once considered a dream, is now a real possibility for future generations. As we gather more data about the heliopause and the interstellar medium, the dream of reaching other star systems becomes ever more tangible. Advances in propulsion systems, spacecraft shielding, and the development of artificial intelligence and robotics will allow for longer and more ambitious missions, such as the search for exoplanets that could harbor life. These missions, which are still in the early planning stages, will likely focus on studying the properties of other star systems and their potential for supporting life. The knowledge gained from studying the heliopause will play a crucial role in understanding how other star systems interact with their surrounding environments, and whether those conditions are conducive to the formation of life. While the heliopause itself may not be the immediate target of human exploration, its study continues to yield important insights that will help shape future space missions. The heliopause, as an interface between our solar system and the broader galaxy, serves as a natural boundary that we must understand if we are to successfully navigate the vast expanse of space. Whether it's the protection it provides from cosmic radiation, the way it shields our solar system from harmful particles, or the insights it offers into the physics of interstellar space, the heliopause remains an essential subject of study for future generations of scientists and explorers. The mystery surrounding the heliopause is one that will continue to captivate researchers for years to come. As technology advances and new data is collected from the Voyager spacecraft and other missions, we can expect our understanding of this boundary to deepen, revealing new layers of complexity and offering fresh perspectives on the nature of space itself. The heliopause, in its enigmatic beauty, stands as both a challenge and an invitation to explore the farthest reaches of the universe, a challenge to understand the forces that shape our solar system and the greater cosmos. As we stand on the precipice of this next great phase of space exploration, one thing is certain: the study of the heliopause will remain an integral part of our quest for knowledge, helping us understand not just our place in the solar system, but our role in the grander tapestry of the universe. The heliopause, as much as it has been studied, still holds many secrets that beg further exploration. One of the most puzzling aspects of this boundary is its role in the broader dynamics of our galaxy. While we understand its basic structure, where the solar wind meets the interstellar medium, we are only scratching the surface of its implications. For example, how does the heliopause affect the trajectory of cosmic rays? Why do some particles seem to slip through its defenses while others are deflected? These questions point to gaps in our understanding of particle physics and magnetic field interactions. The magnetic fields at the heliopause are particularly intriguing. Voyager 1 and 2 have provided data suggesting that these fields may twist and warp as they interact with both the solar wind and the interstellar medium. This interaction generates complex patterns of turbulence, which could have far-reaching consequences for the solar system's stability. Understanding these patterns is not just a matter of academic curiosity. It could have practical implications for future space missions. If spacecraft are to travel beyond the heliopause, they must contend with these turbulent fields, which could disrupt navigation and communication systems. Another mystery involves the temperature gradients at the heliopause. One might expect the temperature to drop significantly as the solar wind slows and merges with the cooler interstellar medium. However, data from the Voyager suggests that the temperature profile is not as straightforward as previously thought. Instead of a smooth transition, there appear to be sharp spikes and drops in temperature, indicating highly localized heating events. These anomalies could be caused by shock waves or particle collisions, but their exact nature remains unclear. Scientists are eager to understand these phenomena, as they could reveal new insights into energy transfer processes in space. The heliopause also serves as a laboratory for studying the fundamental properties of plasma. Plasma, a state of matter composed of charged particles, dominates the heliosphere and much of the universe. By examining how plasma behaves at the heliopause, researchers can test theories about magnetic reconnection, a process where magnetic field lines break and reconnect, releasing vast amounts of energy. Magnetic reconnection is thought to play a key role in phenomena such as solar flares and auroras, making the heliopause an invaluable testing ground for these ideas. As the Voyager probes continue their journey, they are venturing into regions of interstellar space that have never been explored. These regions contain clues about the galaxy's history, including remnants of ancient supernovae. Supernovae, the explosive deaths of massive stars, release shock waves that ripple through the interstellar medium, shaping its structure and composition. By studying the particles and magnetic fields beyond the heliopause, scientists can trace the echoes of these distant cosmic events, piecing together a more complete picture of the galaxy's evolution. The heliopause is also a key point of interest for understanding the Oort cloud, a vast, spherical shell of icy objects that is thought to surround the solar system. While the Oort cloud lies far beyond the heliopause, the two regions are connected in subtle ways. For instance, the heliosphere's shape and behavior could influence the trajectories of comets originating from the Oort cloud. Similarly, the interaction between the solar wind and interstellar medium could affect the dynamics of this distant reservoir of comets, potentially triggering periodic influxes of these icy bodies into the inner solar system. The study of the heliopause is not limited to its physical and magnetic properties. It also has profound implications for the search for extraterrestrial life. The boundary serves as a shield, protecting the solar system from a significant portion of galactic radiation. This protection has likely played a role in the development of life on Earth by reducing the intensity of harmful cosmic rays. Understanding how the heliopause functions as a protective barrier could inform our search for habitable planets around other stars. If similar boundaries exist around other stellar systems, they could provide clues about the conditions necessary for life to thrive. One of the most exciting possibilities for future research is the development of new probes specifically designed to study the heliopause and beyond. While the Voyager spacecraft have provided invaluable data, they were not originally intended for this purpose. Future missions could include advanced instruments capable of mapping the heliopause in greater detail, measuring its fluctuations over time, and analyzing the composition of interstellar particles. These missions could also employ propulsion systems that allow for faster travel, enabling them to reach and study the heliopause more efficiently. In addition to new spacecraft, advancements in ground-based and space-based telescopes could enhance our understanding of the heliopause. Instruments capable of detecting and analyzing cosmic rays, neutral atoms, and other particles from interstellar space could provide complementary data to the measurements taken by spacecraft. By combining these observations, scientists could build a more comprehensive model of the heliopause and its role in the broader galactic environment. The heliopause is not just a boundary, it is a gateway to the unknown. It represents the edge of the solar system, the point where our sun's influence gives way to the vast expanse of interstellar space. But it is also a reminder of how much we have yet to learn about the universe. Each new discovery about the heliopause opens up new questions, challenging our understanding of space and inspiring us to look beyond our current horizons. As we continue to study the heliopause, we are not just learning about a distant region of space, we are laying the groundwork for the future of exploration. The knowledge we gain will inform the design of interstellar missions, guide our search for habitable worlds, and deepen our understanding of the forces that shape the cosmos. The heliopause is a testament to humanity's enduring curiosity and our relentless drive to explore the unknown. The heliopause mysteries extend beyond its physical properties, delving into the nature of cosmic interactions on a grand scale. To understand its role fully, we must consider how it fits within the larger galactic ecosystem. The solar system is not isolated, it is part of the Milky Way galaxy, which teems with stars, interstellar clouds, and cosmic phenomena. The heliopause acts as a dynamic interface between the solar system and this bustling galactic environment. By studying this boundary, scientists can uncover the complex interplay of forces shaping both our local space and the broader galaxy. One significant area of interest is how the heliopause interacts with interstellar clouds. These vast regions of gas and dust drift through the galaxy, and the solar system periodically passes through them during its journey around the Milky Way. When this happens, the heliosphere may compress or expand, depending on the density and pressure of the cloud. Such changes could have dramatic effects on the solar wind, the heliopause, and even conditions within the inner solar system. For instance, a dense interstellar cloud could enhance the flux of cosmic rays penetrating the heliosphere, potentially impacting Earth's climate and biosphere. The heliopause also offers a unique vantage point for studying the interstellar medium itself. This medium, composed of gas, dust, and magnetic fields, fills the space between stars and plays a crucial role in the galaxy's evolution. By analyzing the particles and fields at the heliopause, researchers can gain insights into the composition and behavior of the interstellar medium. This information is invaluable for understanding processes such as star formation, supernovae, and the distribution of elements across the galaxy. One of the most intriguing questions about the heliopause is its shape. Early models depicted it as a relatively spherical boundary, but more recent data suggest that it is highly asymmetrical. This asymmetry is likely due to the influence of the interstellar medium, which exerts uneven pressure on the heliosphere. The solar system's motion through the galaxy adds another layer of complexity, creating a bow shock or a bow wave, similar to the wake of a boat moving through water, on the leading edge of the heliosphere. Understanding this shape is not just an academic exercise. It has implications for how the heliosphere interacts with the galactic environment and how it protects the solar system from cosmic radiation. The role of the heliopause in filtering cosmic rays is another area of intense study. Cosmic rays are high-energy particles that originate from outside the solar system, often from supernova explosions or other energetic events. These particles pose a significant threat to both astronauts and spacecraft, as they can penetrate shielding and cause damage to biological tissues and electronic systems. The heliopause serves as a first line of defense, slowing and deflecting many of these particles before they reach the inner solar system. However, the effectiveness of this shield depends on factors such as the solar wind's strength and the heliosphere's size and shape. By studying the heliopause, scientists can improve models of cosmic ray propagation and develop better strategies for protecting future space travelers. The magnetic fields at the heliopause are another area ripe for exploration. These fields are generated by the interaction of the solar wind's magnetic field with the interstellar medium's magnetic field. The resulting patterns are complex and often unpredictable, with regions of magnetic reconnection, turbulence, and other phenomena. Magnetic reconnection, in particular, is a process of great interest to physicists, as it involves the conversion of magnetic energy into kinetic and thermal energy. This process is not only important for understanding the heliopause but also for studying phenomena such as solar flares, auroras, and even the behavior of plasma in laboratory settings. Another fascinating aspect of the heliopause is its potential to serve as a natural boundary marker for interstellar exploration. As humanity begins to venture beyond the solar system, the heliopause represents a logical milestone. It is the point where the solar wind peters out, and the spacecraft must contend with the uncharted environment of interstellar space. Understanding the conditions at the heliopause will be crucial for designing future missions, as spacecraft will need to navigate through turbulent magnetic fields, fluctuating particle densities, and other challenges. The heliopause also has implications for the search for extraterrestrial intelligence, SETI. One of the key challenges in SETI is distinguishing between natural and artificial signals. The heliopause, with its complex interactions and emissions, could serve as a natural testbed for developing techniques to identify and analyze signals from distant civilizations. By studying the heliopause emissions, scientists can refine their methods for detecting faint, distant signals amidst the cosmic noise. In the broader context of space exploration, the heliopause symbolizes the transition from the known to the unknown. It is a boundary not just in a physical sense but also in a conceptual one. Crossing it represents a leap into interstellar space, where humanity will encounter entirely new phenomena and challenges. The data collected by the Voyager probes have already revolutionized our understanding of this region, but they are just the beginning. Future missions, equipped with more advanced instruments, will undoubtedly uncover even more surprises. The heliopause is a reminder of the interconnectedness of the cosmos. It is not an isolated feature but a dynamic part of a vast and intricate system. Studying it helps us understand not only our solar system but also the galaxy and universe as a whole. It challenges us to think on a cosmic scale, to consider the forces and interactions that shape the cosmos, and to envision humanity's place within this grand tapestry. As we continue to explore the heliopause and its mysteries, we are not just pushing the boundaries of science, we are expanding the boundaries of human imagination. Each discovery brings us closer to answering the fundamental questions about our origins, our place in the universe, and our future as a species. The heliopause is more than just a boundary. It is a gateway to a new frontier, one that promises to inspire generations of explorers, scientists, and dreamers. The heliopause remains one of the most compelling subjects in the study of space due to its complexity and its position as the outermost layer of the solar system's bubble. This region serves as the ultimate battleground between the solar wind and the interstellar medium, offering profound insights into how stellar systems interact with their galactic environments. But as researchers probe deeper into its mysteries, they uncover layers of questions that reshape our understanding of space, energy, and the vast forces at play in the universe. One particularly intriguing topic is how the heliopause influences the distribution and movement of energetic neutral atoms, ENAs. ENAs are produced when charged particles from the solar wind collide with neutral atoms in the interstellar medium. These collisions strip the charged particles of their electric charge, transforming them into neutral atoms that can travel long distances unaffected by magnetic fields. By analyzing the patterns of these ENAs, scientists can essentially map the heliopause and its surrounding regions. Missions like NASA's Interstellar Boundary Explorer, IBEX, and the upcoming Interstellar Mapping and Acceleration Probe, IMAP, have been pivotal in creating these detailed maps, revealing the heliopause's dynamic and uneven structure. These ENA maps have already provided unexpected discoveries. For instance, researchers identified a mysterious ribbon of enhanced ENA emissions that stretches across the sky near the heliopause. This ribbon is believed to be caused by interactions between the solar wind and the galactic magnetic field, but its exact origin and structure remain a subject of intense study. This phenomenon underscores the complexity of the heliopause and highlights how much we still have to learn about this boundary. The shape of the heliosphere itself, which directly influences the heliopause, continues to challenge our expectations. As the solar system moves through the galaxy, it encounters varying conditions in the interstellar medium, such as changes in density, magnetic fields, and pressure. These variations can cause the heliosphere to take on different shapes, sometimes elongated, sometimes more compact. Recent evidence suggests that the heliosphere may not have a tail-like structure, as previously thought, but could instead resemble a croissant or other more intricate forms. These findings challenge traditional models and open new questions about how solar systems interact with their environments. Another aspect of the heliopause that fascinates scientists is its role as a boundary layer for cosmic rays. While the heliosphere acts as a shield, the heliopause itself represents a zone of heightened interaction where galactic cosmic rays and solar particles collide. These interactions can create unique radiation environments that differ from those inside or outside the heliosphere. By studying these zones, scientists can better understand the processes that govern cosmic ray propagation, which has implications for everything from space exploration to understanding the universe's most energetic phenomena. The Voyager probe's journey through the heliopause also revealed surprises about the region's magnetic fields. Voyager 1, for instance, detected a puzzling alignment between the solar magnetic field and the interstellar magnetic field at the heliopause. This alignment was unexpected, as many models had predicted a sharp discontinuity or significant differences between the two fields. This discovery suggests that the heliopause may play a role in shaping or mediating magnetic fields on a broader scale, potentially influencing cosmic rays and other particles far beyond the solar system. The study of the heliopause is not limited to its physical and magnetic properties. It also provides a unique laboratory for testing theories of astrophysics and plasma dynamics. The interactions between the solar wind and the interstellar medium involve complex processes such as turbulence, magnetic reconnection, and particle acceleration. These processes occur on scales that are difficult to replicate in laboratory settings, making the heliopause an invaluable natural laboratory for studying these phenomena in their full cosmic context. As we develop more sophisticated technologies, our ability to study the heliopause will only improve. Future missions aimed at exploring the interstellar medium will likely include instruments specifically designed to probe the heliopause in greater detail. These missions could provide high-resolution measurements of particle densities, magnetic fields, and other properties, offering a more comprehensive picture of this dynamic boundary. Additionally, advancements in computational modeling will enable researchers to simulate the heliopause and its interactions with unprecedented accuracy, helping to interpret observational data and predict future discoveries. The heliopause also has implications for understanding other star systems. While our solar system's heliopause is unique in its specific characteristics, the processes that shape it are thought to be universal. By studying the heliopause, we can gain insights into how other stars interact with their galactic environments, shedding light on the diversity of heliospheres and their potential impact on exoplanets. For example, understanding the protective role of a star's heliosphere could help assess the habitability of planets orbiting other stars. A robust heliosphere might shield planets from harmful cosmic radiation, while a weaker one could leave them more exposed. One of the most exciting possibilities for future research is the potential to send spacecraft beyond the heliopause to explore interstellar space directly. While the Voyager probes have provided invaluable data, they were not designed for extended interstellar missions. A dedicated interstellar probe, equipped with state-of-the-art instruments, could provide a wealth of information about the heliopause, the interstellar medium, and the broader galactic environment. Such a mission would represent a monumental step in humanity's exploration of the cosmos, pushing the boundaries of what is possible and expanding our understanding of the universe. The heliopause is more than just a boundary. It is a testament to the interconnectedness of all things in the cosmos. It is a dynamic, ever-changing region that reflects the interplay of forces on both a local and galactic scale. By studying it, we not only learn about our own solar system but also gain a deeper appreciation for the complex web of interactions that shape the universe. Each discovery at the heliopause brings us closer to answering fundamental questions about our place in the cosmos and our relationship with the broader galaxy. In the grand scheme of things, the heliopause serves as a reminder of the vastness and complexity of the universe. It is a boundary that challenges our understanding, inspires our curiosity, and fuels our desire to explore. As we continue to probe its mysteries, we are not just seeking answers about the heliopause itself. We are striving to unlock the secrets of the cosmos and our place within it. The journey is far from over, and the discoveries yet to come promise to be as transformative as those that have already been made. The heliopause, in all its complexity and beauty, stands as a gateway to the stars, inviting us to explore, to question, and to dream. The heliopause represents the outermost frontier of our solar system's direct influence, yet it is also a microcosm of the universal forces that govern the cosmos. To truly grasp its importance, we must delve deeper into the science, the implications, and the philosophical questions it raises about humanity's place in the universe. One of the most compelling aspects of the heliopause is how it reflects the dynamic and sometimes chaotic balance between the solar wind and the interstellar medium. The solar wind, a constant stream of charged particles emitted by the sun, travels outward in all directions, shaping the heliosphere as it pushes against the surrounding interstellar material. However, this flow is neither uniform nor constant. Solar activity, including solar flares and coronal mass ejections, causes fluctuations in the solar wind's intensity, creating ripple effects that propagate through the heliosphere and ultimately impact the heliopause. This variability in the solar wind introduces a level of complexity to the heliopause structure. Instead of being a static boundary, the heliopause is a constantly shifting region that responds to changes in solar activity and the interstellar medium. For instance, during periods of high solar activity, the increased pressure from the solar wind can push the heliopause outward, expanding the boundaries of the heliosphere. Conversely, during solar minimum, when the sun's activity is at its lowest, the heliopause contracts, allowing interstellar particles to penetrate closer to the solar system. These dynamics have significant implications for understanding how solar systems interact with their galactic environments. By studying the heliopause, scientists can develop models to predict how other stars and their planetary systems might behave under similar conditions. This research is crucial for identifying potentially habitable exoplanets, as the heliosphere's protective effects against cosmic radiation are a key factor in determining the habitability of planets within a solar system. Another fascinating aspect of the heliopause is its role as a natural particle accelerator. The interactions between the solar wind and the interstellar medium create turbulent regions where charged particles are accelerated to high energies. These regions are of particular interest to astrophysicists because they provide a glimpse into the mechanisms that drive cosmic ray acceleration throughout the galaxy. By studying the heliopause, researchers can gain insights into how similar processes occur in supernova remnants, active galactic nuclei, and other extreme astrophysical environments. The Voyager missions have been instrumental in uncovering these phenomena. Voyager 1, which crossed the heliopause in 2012, detected a sudden drop in solar wind particles and a corresponding increase in galactic cosmic rays, confirming its entry into interstellar space. However, the transition was not as straightforward as scientists had anticipated. Instead of a sharp boundary, Voyager 1 encountered a complex, layered region where particles from the solar wind and the interstellar medium mingled. This discovery challenged existing models and highlighted the need for more advanced instruments to study the heliopause in greater detail. Voyager 2, which followed in 2018, provided additional data that further complicated our understanding of the heliopause. Unlike Voyager 1, which crossed the boundary in a relatively calm region, Voyager 2 encountered a more turbulent environment with significant variations in particle densities and magnetic fields. These differences suggest that the heliopause is not uniform but varies depending on the direction and local conditions of the interstellar medium. This finding underscores the importance of studying multiple regions of the heliopause to develop a comprehensive understanding of its structure and behavior. Beyond the physical and magnetic properties of the heliopause, its study also raises profound questions about the nature of space exploration and humanity's relationship with the universe. The heliopause represents the limit of the Sun's influence, but it is not a hard boundary. Instead, it is a transitional region where the familiar environment of the solar system gives way to the vast, uncharted expanse of interstellar space. This transition challenges our perceptions of boundaries and invites us to consider the interconnectedness of all things in the cosmos. In a broader sense, the heliopause serves as a metaphor for exploration and discovery. Just as the Voyager probes ventured into the unknown, crossing the heliopause represents humanity's first steps into the interstellar realm. It is a reminder that while we may be confined to a single planet for now, our curiosity and ingenuity have the power to transcend even the most formidable barriers. The data sent back by Voyager 1 and 2, traveling at speeds of over 17 kilometers per second, is a testament to the enduring legacy of human exploration and our desire to understand the universe. As we look to the future, the study of the heliopause will continue to evolve with advancements in technology and new mission concepts. One promising idea is the development of an interstellar probe specifically designed to study the heliopause and the surrounding interstellar medium. Such a mission could carry advanced instruments capable of measuring magnetic fields, particle densities, and radiation levels with unprecedented precision. It could also provide high-resolution images of the heliopause and its interactions with the interstellar medium, offering a more detailed view of this enigmatic boundary. In addition to robotic missions, the heliopause also presents opportunities for collaborative research involving ground-based observatories and space telescopes. By combining data from multiple sources, scientists can develop more accurate models of the heliopause and its interactions with the galactic environment. These efforts will not only enhance our understanding of the heliopause but also contribute to broader studies of astrophysics, plasma physics, and cosmic ray propagation. The heliopause also has implications for the future of human space exploration. As we venture further into space, understanding the heliopause and its protective effects will be crucial for designing spacecraft and habitats capable of withstanding the harsh conditions of interstellar travel. The heliopause marks the beginning of a new era of exploration, one that will require innovative solutions to overcome the challenges of traveling beyond the solar system. The heliopause is far more than just a boundary. It is a dynamic and complex region that holds the key to understanding the interplay between solar systems and the galaxy. Its study has already revealed groundbreaking discoveries, from the unexpected structure of the heliosphere to the intricate interactions between solar and interstellar particles. As we continue to explore this frontier, we are not only uncovering the secrets of the heliopause but also paving the way for humanity's journey into the stars. The heliopause is a testament to the power of curiosity and the human spirit of exploration. It challenges us to push the limits of what we know and to venture into the unknown with an open mind and a sense of wonder. In its complexity and beauty, it reminds us that the universe is vast, mysterious, and full of possibilities waiting to be discovered. The heliopause also acts as a natural observatory of cosmic interactions, offering a unique opportunity to study how two distinct astrophysical environments meet and merge. On one side, the heliosphere carries the signature of the Sun's activities, shaped by millions of years of solar wind streaming outward. On the other, the interstellar medium embodies the remnants of ancient stars and the collective influences of galactic processes. This interplay is like a grand cosmic handshake, an intersection that tells the story of our Sun's place in the galaxy and the forces that shape our universe on a larger scale. The magnetic fields at the heliopause further deepen the intrigue. The Sun's magnetic field, carried outward by the solar wind, interacts with the interstellar magnetic field in ways that scientists are still working to decode. Voyager data showed that these fields don't simply align or oppose one another, they twist, distort, and create complex patterns that scientists describe as magnetic draping. This phenomenon has implications far beyond the solar system, shedding light on how magnetic fields behave in other star systems, and even in the spaces between galaxies. One of the most surprising discoveries made by the Voyager probes was the so-called magnetic highway, a region just before the heliopause where charged particles from inside and outside the heliosphere could freely exchange. This unexpected region revealed that the heliosphere is not as isolated as once believed. Instead, there appears to be a porous quality to this boundary, with particles and energy flowing in both directions. This discovery challenged the notion of the heliopause as a one-way exit and suggested that the solar system is in constant dialogue with its galactic surroundings. As scientists have examined these findings, they've begun to reconsider long-held assumptions about the role of the heliosphere in shielding our solar system. It was traditionally believed that the heliosphere serves as a protective bubble, deflecting most of the cosmic rays and high-energy particles originating from outside the solar system. However, the Voyager probes revealed that while the heliosphere does offer some protection, it is not an impenetrable barrier. Instead, the heliopause allows for a gradual mixing of solar and interstellar particles, creating a complex environment where cosmic rays can leak through. This revelation has practical implications for human space exploration. As humanity contemplates sending crewed missions beyond the heliosphere, whether to nearby stars or interstellar space, understanding the radiation environment becomes a matter of life and death. The heliopause marks the end of the Sun's protective influence, meaning that spacecraft and astronauts traveling beyond it would be exposed to far higher levels of cosmic radiation. This reality underscores the importance of studying the heliopause not just for scientific curiosity but for preparing humanity's future in space. The Voyager probes themselves are poignant symbols of this future. Each spacecraft carries a golden record, a time capsule of sounds and images from Earth meant to represent humanity to any extraterrestrial civilization that might encounter it. These records, attached to probes traveling through interstellar space, are humanity's first physical emissaries to the wider galaxy. The fact that they crossed the heliopause during their journeys lends a poetic symmetry to their mission. They are not just leaving the solar system, they are entering the realm where the Sun's influence fades, becoming true explorers of the unknown. The data collected by the Voyager missions have sparked numerous debates and unanswered questions among scientists. For instance, why does the heliopause appear to have such a complex and varied structure? Are the observed differences between Voyager 1's and Voyager 2's crossings due to inherent variability in the interstellar medium? Or do they reflect asymmetries in the heliosphere itself? What role do interstellar magnetic fields play in shaping the boundary? And how do these fields interact with the solar wind over long periods? Answering these questions will require more than just Voyager data. Future missions to the heliopause and beyond will need to incorporate advanced technology capable of capturing high-resolution measurements of magnetic fields, particle flows, and radiation levels. Concepts like the interstellar probe, proposed by NASA and other agencies, aim to carry modern instruments far beyond the heliopause to study interstellar space in unprecedented detail. These missions could also include imaging systems to capture visual data of the heliosphere's boundary, allowing scientists to map its shape and structure more comprehensively. Additionally, the heliopause offers a testing ground for theories about the behavior of plasma, a state of matter that makes up the majority of the visible universe. The interaction between solar and interstellar plasma at the heliopause mirrors processes observed in more extreme environments, such as the accretion disks around black holes or the jets of active galaxies. By studying the relatively accessible environment of the heliopause, scientists can refine their models of plasma physics and apply these insights to more distant and exotic phenomena. One intriguing idea involves the possibility of using the heliopause as a natural laboratory for understanding the origins of cosmic rays. These high-energy particles, some of which travel from distant galaxies, are thought to gain their incredible speeds through processes occurring in shock fronts and magnetic fields. The heliopause, with its turbulent boundary regions, may serve as a microcosm of these larger processes, allowing researchers to test hypotheses about how cosmic rays are accelerated and propagated across the universe. The philosophical implications of the heliopause cannot be overstated. It represents a boundary that is both literal and metaphorical, a place where humanity must confront its limitations and its potential. On one hand, the heliopause marks the end of our sun's reach, a reminder of how small and finite our solar system is within the vastness of the Milky Way. On the other hand, it symbolizes the beginning of a new frontier, a place where human curiosity and ingenuity can push beyond the known and into the infinite. The Voyager probes, now traveling through interstellar space, are a testament to this duality. They carry the legacy of human achievement, while venturing into realms where no human-made object has ever gone before. Their journeys remind us that while the heliopause may represent the edge of our sun's influence, it is not the edge of human potential. It is merely the next step in a long journey of discovery that began when our ancestors first looked up at the stars and wondered what lay beyond. In many ways, the heliopause is a mirror. It reflects not just the forces that shape our solar system but also the questions that drive humanity's exploration of the cosmos. What lies beyond the boundaries we know? How do we fit into the larger universe? And what will we discover when we cross the next threshold? As technology advances and our understanding deepens, the heliopause will continue to be a focus of scientific inquiry and a source of inspiration. It challenges us to think big, to push the limits of what we know, and to embrace the unknown with curiosity and courage. And as we continue to study this fascinating boundary, we are reminded that the journey to understand the universe is as infinite as the universe itself. The heliopause, as a region of transition, not only reveals the intricate details of our sun's influence but also poses questions that redefine our understanding of space and time. As Voyager 1 and 2 continue their silent voyages into interstellar space, they serve as living experiments, continuously feeding humanity with data from the uncharted frontier. Every bit of information they send back deepens the mystery and opens doors to new scientific investigations, challenging our assumptions and pushing the boundaries of human knowledge. One of the most fascinating aspects of the heliopause is how it relates to the broader dynamics of the Milky Way galaxy. The solar system travels through the galaxy like a ship sailing through a cosmic ocean. The heliosphere acts as the ship's hull, protecting its precious cargo from the harsher elements of the interstellar medium. But this metaphor raises critical questions. How does the heliosphere's movement affect its shape? Does it act as a wake, leaving disturbances behind it? And how does this interaction change over millions of years as the Sun moves through different regions of the galaxy? The interstellar medium itself is far from uniform. It is a dynamic and turbulent environment filled with clouds of gas, magnetic fields, and cosmic rays. As the solar system moves through this medium, the heliopause responds to these changes. It may expand or contract, becoming more or less porous depending on the density and energy of the interstellar particles it encounters. Voyager's observations have provided some hints about these interactions, but they've also raised more questions than answers. For instance, why do certain areas of the heliopause appear denser than others? Is this due to the Sun's variable output, or are we seeing the influence of distant interstellar events, such as supernovae, rippling through the galaxy? The shape of the heliosphere is another topic of intense debate. For decades, it was assumed to be roughly spherical, with the Sun at its center. However, data from Voyager and other missions suggest a more complex structure. Some models propose a teardrop shape, with a rounded front facing the direction of the solar system's movement, and a long tail trailing behind. Others suggest a croissant-like structure, shaped by the interplay of solar and interstellar magnetic fields. Understanding the true shape of the heliosphere is not just an academic exercise. It has practical implications for predicting how cosmic radiation interacts with our solar system and affects planetary environments. This brings us to the concept of interstellar weather. Just as Earth experiences weather patterns driven by atmospheric dynamics, the heliosphere is influenced by the weather of the interstellar medium. These conditions can include shock waves from distant supernovae, changes in the galactic magnetic field, or variations in cosmic ray intensity. Each of these factors can alter the heliopause, making it a dynamic and ever-changing boundary rather than a static shell. By studying these interactions, scientists can gain insights into the broader processes that shape our galaxy and influence the habitability of planetary systems. The Voyager missions have also highlighted the role of the heliopause as a laboratory for studying cosmic particle acceleration. As charged particles approach the heliopause, they encounter shock waves and magnetic turbulence that can increase their energy levels. This process, known as Fermi acceleration, is believed to occur on much larger scales in supernova remnants and active galactic nuclei. By observing it in the relatively accessible environment of the heliopause, scientists can test theories and refine models that apply to these distant and extreme phenomena. Another unexpected discovery from Voyager data is the presence of interstellar pressure waves. These waves, caused by variations in the interstellar medium, appear to compress and distort the heliopause, creating ripples that propagate through the boundary. These pressure waves offer a unique opportunity to study the mechanics of plasma and magnetic fields in a relatively controlled setting, providing a microcosm of the forces that shape the larger universe. Looking ahead, the next generation of missions to the heliopause will likely include advanced technologies to address questions that the Voyager probes were not equipped to answer. For instance, modern instruments could measure the precise composition of interstellar particles, providing clues about the chemical and isotopic makeup of the galaxy. High-resolution imaging systems could capture detailed views of the heliopause structure, offering visual confirmation of its shape and dynamics. And new methods of data transmission could allow for real-time monitoring of changes at the boundary, giving scientists an unprecedented level of detail about this critical region. As we continue to study the heliopause, it's worth reflecting on its symbolic significance. It represents the edge of the known, a place where the familiar meets the unknown. For centuries, humanity has been driven by a desire to explore such boundaries, whether crossing oceans, scaling mountains, or venturing into space. The heliopause is the latest, and perhaps most profound, frontier in this ongoing journey. It's also a reminder of our interconnectedness with the cosmos. The particles streaming through the heliopause are the remnants of ancient stars, the building blocks of galaxies, and the seeds of future solar systems. They tell a story of cycles and transformations that spans billions of years and countless light years. By studying the heliopause, we're not just learning about our solar system, we're connecting with the larger narrative of the universe itself. And yet, for all we've learned, the heliopause remains a place of mystery. Every new discovery seems to raise new questions, each more tantalizing than the last. What lies beyond the heliosphere? How do interstellar processes shape the boundaries of other star systems? And what will we find as we continue to push outward, into the uncharted depths of space? These questions are not just scientific, they are deeply human. They speak to our curiosity, our imagination, and our desire to understand our place in the universe. The heliopause is more than just a physical boundary, it is a testament to the human spirit, a symbol of our drive to explore, to learn, and to dream. As the Voyager probes continue their silent journey into interstellar space, they carry with them a message of hope and curiosity, a reminder that no boundary is final, and that the quest for knowledge is as infinite as the cosmos itself. And as we look to the future, the heliopause will remain a beacon, guiding us toward new discoveries and inspiring us to keep asking the questions that define what it means to be human. The heliopause is not only a symbol of exploration but also a real, dynamic frontier that challenges everything we thought we knew about our solar system and the galaxy beyond. As we delve deeper into its mysteries, one thing becomes clear: the heliopause is more than a boundary. It's a living, breathing interface, a place where the immense forces of the Sun and the galaxy collide and mingle in ways that are as beautiful as they are complex. Voyager's passage into interstellar space has provided us with clues, but it has also laid the groundwork for an entirely new era of exploration. Imagine future spacecraft equipped with instruments far more sensitive and advanced than anything we have today, capable of not just crossing the heliopause but also lingering there, studying its every fluctuation, particle, and wave. These future missions could focus on mapping the shape of the heliopause in 3 dimensions, offering a clearer picture of its structure and how it interacts with the interstellar medium. But the importance of studying the heliopause extends beyond the solar system. It serves as a reference point for understanding other stellar systems scattered throughout the Milky Way. Every star has its version of a heliopause, a region where its stellar wind meets the interstellar medium. By comparing our heliopause with those of other stars, scientists can gather insights into the variability of stellar systems and how they might affect the habitability of planets orbiting within them. For instance, stars more massive or active than our Sun likely have much larger and more energetic heliospheres. These could either provide better shielding against cosmic rays or create more turbulent environments that make planetary development more challenging. On the other hand, smaller stars like red dwarfs, which are abundant in the galaxy, may have much smaller heliospheres, exposing their planets to higher levels of cosmic radiation. Understanding these differences could help us narrow down the search for potentially habitable exoplanets. There's also the question of how the Sun's motion through the galaxy influences the heliopause over vast timescales. Our solar system isn't stationary. It's hurtling through the Milky Way at an average speed of about 828,000 kilometers per hour. Over the course of millions of years, the solar system passes through different regions of the galaxy, each with its own unique characteristics. Some areas may have denser interstellar clouds, while others are relatively empty. These changes can dramatically alter the shape and size of the heliosphere, as well as the conditions at the heliopause. For example, during periods when the solar system moves through dense interstellar clouds, the heliopause might shrink significantly, allowing more cosmic rays to penetrate into the inner solar system. This could have profound implications for Earth's climate, and even for the evolution of life. In contrast, during times when the solar system travels through less dense regions, the heliopause might expand, offering greater protection. Studying these changes could give us a better understanding of how the Sun's journey through the galaxy has shaped the history of our planet. The heliopause also holds the key to understanding the interstellar medium itself. Voyager has already detected unexpected variations in the density and pressure of interstellar particles near the heliopause. These observations suggest that the interstellar medium is far from uniform. It's a patchwork of different densities, temperatures, and magnetic fields. By studying how the heliopause reacts to these variations, scientists can gain valuable insights into the large-scale structure and dynamics of the Milky Way. One of the most intriguing discoveries made by Voyager is the detection of interstellar magnetic fields near the heliopause. These fields are thought to play a critical role in shaping the boundary and influencing the behavior of charged particles. However, their exact nature remains poorly understood. Are they remnants of ancient supernova explosions, or do they arise from more localized processes within the galaxy? Answering these questions could shed light on the broader magnetic architecture of the Milky Way and its role in shaping galactic ecosystems. Another area of interest is the interaction between the heliopause and cosmic rays, high-energy particles that originate from distant astrophysical sources like supernovae and black holes. The heliopause acts as a barrier to these particles, but it's not impenetrable. Some cosmic rays manage to cross into the solar system, where they can have significant effects on planetary atmospheres and even on living organisms. Understanding how the heliopause filters cosmic rays is crucial for fields ranging from climate science to astrobiology. In the future, scientists hope to develop more sophisticated models of the heliopause that incorporate data from a variety of sources, including not just Voyager but also newer missions like the Interstellar Mapping and Acceleration Probe, IMAP. IMAP, scheduled for launch in the coming years, aims to study the interactions between the solar wind and the interstellar medium in unprecedented detail. Its findings could help refine our understanding of the heliopause and its role in the broader galactic environment. But perhaps the most exciting prospect is the possibility of sending a dedicated interstellar probe specifically designed to study the heliopause and beyond. Such a mission could carry advanced instruments capable of analyzing the composition of interstellar particles, mapping magnetic fields, and even capturing images of the heliopause itself. It could linger at the boundary for extended periods, providing a continuous stream of data that would revolutionize our understanding of this enigmatic region. As we contemplate these future missions, it's worth remembering that the heliopause is more than just a scientific curiosity. It's a reminder of humanity's ability to reach beyond the known and venture into the unknown. It represents the culmination of centuries of curiosity and ingenuity, from the earliest stargazers to the engineers who built the Voyager probes. And as we continue to explore this boundary, we're not just expanding our knowledge of the cosmos, we're affirming our place within it. The heliopause challenges us to think big, to ask bold questions, and to embrace the mysteries that lie beyond our current understanding. It's a frontier that beckons us to keep exploring, to keep pushing the boundaries of what we know, and to keep dreaming of what lies beyond. The heliopause stands as an emblem of how humanity's thirst for discovery constantly drives us to uncover the secrets of the universe. It isn't just a physical boundary, it's a marker of how far we've come as a civilization, both in terms of technological achievements and our understanding of the cosmos. The knowledge we've gained from the Voyager missions is just the beginning. Every observation, every anomaly, and every question raised by these spacecraft has sparked further curiosity, ensuring that our journey of exploration will continue for generations to come. One of the most fascinating aspects of the heliopause is its dynamic nature. This boundary is not a fixed wall. It fluctuates, breathes, and reacts to changes in the environment. For instance, the solar wind's intensity varies depending on the sun's activity cycle. During solar maximum, when the sun is most active, the increased solar wind pressure can push the heliopause outward, expanding the reach of the heliosphere. Conversely, during solar minimum, the reduced solar wind pressure allows the heliopause to contract. This pulsating motion, driven by the rhythms of our sun, makes the heliopause a living, ever-changing entity. Adding to this complexity is the interaction between the heliosphere and interstellar magnetic fields. Voyager has detected regions of increased magnetic pressure near the heliopause, which suggests that these fields play a significant role in shaping the boundary. These magnetic interactions are far more intricate than initially thought, involving a delicate balance of forces that scientists are only beginning to understand. Studying these magnetic interactions could provide clues about the larger-scale magnetic environment of the Milky Way and how it influences the behavior of stars and planets. The heliopause is also a critical filter for galactic cosmic rays. These high-energy particles, which originate from powerful events like supernovae, pose a significant challenge for understanding the radiation environment of our solar system. The heliopause blocks some cosmic rays but allows others to penetrate into the inner solar system. Voyager's observations have shown that the heliopause is not a perfect shield. Cosmic ray intensity changes dramatically as the probes cross this boundary. Understanding how cosmic rays interact with the heliopause is essential for preparing future space missions and assessing the risks of radiation exposure for astronauts. Beyond cosmic rays, the heliopause offers a window into the nature of the interstellar medium itself. This vast expanse of gas, dust, and magnetic fields fills the space between stars and plays a crucial role in the life cycle of galaxies. By studying the particles and fields near the heliopause, scientists can gain insights into the composition and dynamics of the interstellar medium. Voyager has already detected variations in the density and temperature of interstellar particles near the heliopause, raising questions about how these properties change across different regions of the galaxy. One of the most profound questions about the heliopause is how it compares to similar boundaries around other stars. Every star generates a stellar wind, creating a heliosphere and a heliopause. By understanding our heliopause, we can develop models that apply to other stellar systems. This comparative approach could reveal how different stars influence their surrounding environments, and what this means for the planets orbiting them. For example, stars with more intense stellar winds might create larger heliospheres, potentially offering greater protection for planets against cosmic rays. On the other hand, stars with weaker winds might expose their planets to harsher radiation environments, influencing the development of life. The heliopause also offers a unique perspective on the Sun's movement through the galaxy. Our solar system is not static, it's constantly moving through the Milky Way, encountering different regions of interstellar space. Some of these regions are denser, while others are more tenuous, and these variations can dramatically affect the shape and size of the heliosphere. Understanding how the heliopause responds to these changes can provide valuable insights into the history of the solar system and its interactions with the galaxy. Future missions to the heliopause and beyond promise to unlock even more of its secrets. For instance, scientists are developing concepts for spacecraft that could travel faster and farther than Voyager, equipped with advanced instruments capable of analyzing the interstellar medium in unprecedented detail. These missions could focus on mapping the three-dimensional structure of the heliopause, studying its magnetic and plasma properties, and identifying how it changes over time. Such missions would not only deepen our understanding of the heliopause but also pave the way for exploring the interstellar medium more comprehensively. One particularly exciting idea is the development of interstellar probes designed to linger at the heliopause, providing continuous data over long periods. These probes could study the boundaries' response to changes in solar activity, variations in the interstellar medium, and interactions with cosmic rays. They could also serve as a stepping stone for even more ambitious missions aimed at exploring nearby star systems. As we look to the future, it's clear that the heliopause is not just a scientific frontier, it's a symbol of humanity's unyielding desire to understand our place in the universe. Every discovery made at this boundary reminds us of the vastness of the cosmos, and the countless mysteries that await beyond it. The heliopause is both a destination and a doorway, marking the edge of one chapter in our exploration of space and the beginning of another. Ultimately, the study of the heliopause is a testament to what we can achieve when we push the boundaries of knowledge. It's a reminder that the universe is far more complex and interconnected than we ever imagined, and that every answer we find leads to new questions. The heliopause may be the edge of the solar system, but it's also the starting point for exploring the galaxy and beyond. The heliopause is not only a boundary in space, it's a symbol of transition, representing the divide between the known and the unknown. It is a place where our understanding of physics, cosmic interactions, and the broader universe is continuously tested and redefined. By delving into its mysteries, we not only learn about the solar system's limits but also uncover clues about the galaxy's dynamic environment. This line between solar wind dominance and interstellar space may seem far removed from our everyday lives, but the knowledge it provides reverberates through every corner of science, shaping our perspective of the cosmos. The Voyager mission's discoveries at the heliopause have led to profound questions about the structure and dynamics of the interstellar medium. For example, what lies beyond this invisible barrier? The interstellar medium is composed of gas, dust, and magnetic fields, but it is far from uniform. It contains regions of varying density and pressure, as well as pockets of turbulence. As Voyager 1 ventured into interstellar space, it encountered a denser region of plasma, suggesting that the medium just beyond the heliopause is far more active than previously thought. These variations could influence the heliopause itself, creating a feedback loop that reshapes the boundary over time. Moreover, the heliopause may not be a simple, smooth structure. Data from Voyager 2 suggests that the heliopause could have a complex, layered architecture, possibly influenced by the interstellar magnetic field and turbulence in the solar wind. This layering effect might create pockets of different plasma densities or magnetic intensities, which in turn could affect how cosmic rays and other energetic particles interact with the heliosphere. Understanding this complexity is critical for developing accurate models of the heliopause and its role in shielding the solar system. Another intriguing aspect of the heliopause is its asymmetry. The Sun's movement through the galaxy, combined with variations in the solar wind and interstellar medium, creates a heliopause that is not spherical but elongated and irregular. This asymmetry raises fascinating questions about how the Sun's galactic environment influences the heliosphere's shape and size. For instance, if the solar system moves into a denser region of interstellar space, the heliopause could contract, potentially exposing the inner solar system to higher levels of cosmic radiation. Conversely, a less dense region could allow the heliopause to expand, enhancing its protective effects. One of the most groundbreaking revelations from the Voyager probes is the presence of interstellar shocks and waves near the heliopause. These phenomena occur when streams of charged particles collide, creating shock fronts that ripple through the interstellar medium. Voyager has detected such shocks, providing direct evidence of dynamic processes occurring at the edge of the solar system. These findings suggest that the heliopause is not a passive boundary but an active participant in the cosmic dance of forces that shape the galaxy. The heliopause also plays a crucial role in understanding the Sun's relationship with the galaxy. The Sun's magnetic field, carried outward by the solar wind, creates a bubble that defines the heliosphere. This bubble interacts with the interstellar medium, creating the heliopause as a sort of membrane between the two. By studying the heliopause, scientists can learn how the Sun influences its surroundings and how the galaxy, in turn, affects the Sun. This two-way interaction has profound implications for astrophysics, shedding light on the mechanisms that govern stellar systems and their environments. Another key mystery is how the heliopause influences the flow of interstellar particles into the solar system. Voyager data have shown that some particles can penetrate the heliopause, while others are deflected. This selective filtering process is not fully understood but likely involves a combination of magnetic fields, particle energies, and the heliopause's dynamic structure. Understanding this process could provide critical insights into the cosmic ray environment of the solar system, which has implications for space exploration and the study of planetary atmospheres. The heliopause is also a window into the early history of the solar system. By analyzing the particles and fields near the heliopause, scientists can infer information about the conditions that existed when the solar system formed. For instance, the composition of interstellar particles can reveal clues about the birth of the Sun and its interaction with the surrounding stellar nursery. These insights can help us piece together the story of how our solar system came to be and how it fits into the broader context of galactic evolution. As humanity looks toward the future, the study of the heliopause will remain a cornerstone of space exploration. Advances in technology promise to revolutionize our understanding of this enigmatic boundary. Future probes equipped with more sensitive instruments could map the heliopause in unprecedented detail, revealing its structure, composition, and interactions with the interstellar medium. These missions could also explore the regions just beyond the heliopause, providing a glimpse into the true nature of interstellar space. One ambitious concept is the development of an interstellar probe designed to operate far beyond the heliopause. Such a mission could study the interstellar medium in situ, providing data that are impossible to obtain from within the heliosphere. This probe could also serve as a testbed for technologies needed for even more distant explorations, such as missions to nearby star systems. By venturing beyond the heliopause, humanity could take its first steps toward becoming an interstellar civilization. The heliopause is a reminder that the universe is far more intricate and interconnected than we often realize. It is a boundary that challenges our understanding of physics, a gateway to the mysteries of the galaxy, and a testament to the power of human ingenuity. As we continue to study this fascinating frontier, we are not just exploring the edge of the solar system, we are uncovering the fundamental truths that define our place in the cosmos. The heliopause serves as a natural laboratory for studying the interplay of forces that define not only our solar system but also countless others across the galaxy. Its study extends far beyond curiosity, This boundary provides a critical testbed for theories of astrophysics, magnetohydrodynamics, and plasma interactions. Every new discovery at the heliopause opens doors to understanding how stars and their surrounding environments evolve over time and space. One of the ongoing debates centers around the interaction between the heliopause and cosmic rays. Cosmic rays are high-energy particles that originate from sources like supernovae, pulsars, and even distant galaxies. The heliopause acts as a partial barrier, but Voyager's data have revealed that it is not entirely impermeable. Some cosmic rays manage to penetrate the heliopause, raising questions about how they interact with the solar wind and magnetic fields. These interactions could provide answers to one of astrophysics' greatest mysteries: the origin and propagation of cosmic rays across the galaxy. Moreover, the heliopause offers unique insights into magnetic reconnection, a phenomenon where magnetic field lines break and reconnect, releasing vast amounts of energy. Voyager's instruments have hinted at reconnection events occurring at or near the heliopause. Understanding these processes could have profound implications not just for space physics but also for terrestrial technologies like nuclear fusion, which relies on controlling plasma behavior. The heliopause is, in essence, a natural plasma physics experiment unfolding billions of miles away. The study of the heliopause also has practical implications for space travel. As humanity dreams of interstellar journeys, understanding the conditions beyond the heliopause becomes vital. The interstellar medium is a harsh environment, filled with energetic particles and radiation that could pose significant challenges to spacecraft and astronauts. By studying the heliopause, scientists can develop better shielding technologies and navigation systems for future missions that venture beyond the solar system. Another fascinating aspect of the heliopause is its connection to the Sun's activity. The solar cycle, an approximately 11-year period of increasing and decreasing solar activity, influences the intensity and reach of the solar wind. During periods of high solar activity, the solar wind can push the heliopause outward, while low activity allows it to contract. This dynamic behavior means that the heliopause is not a static boundary but a living, breathing structure that responds to the Sun's rhythms. Understanding these changes could help predict how the heliosphere will evolve over time, providing a window into the future of our solar system. The shape of the heliopause is another area ripe for exploration. While Voyager's data suggests that the heliopause is elongated, its exact shape remains uncertain. Some models propose a teardrop shape caused by the Sun's motion through the galaxy, while others suggest a more complex, asymmetrical structure influenced by the interstellar magnetic field. Future missions equipped with advanced sensors could map the heliopause in 3 dimensions, providing a clearer picture of its true form and the forces that shape it. The heliopause also raises profound philosophical questions about the nature of boundaries in the universe. It is a physical barrier, yes, but it is also symbolic. It represents the limit of the Sun's influence, the edge of the bubble in which humanity evolved and thrived. Beyond it lies the vast, uncharted expanse of interstellar space, a realm that has existed for billions of years and will continue to exist long after the Sun has burned out. Studying the heliopause is a reminder of our place in the cosmos, a humbling acknowledgement of the vastness that surrounds us. Voyager's journey to the heliopause and beyond has also ignited a sense of wonder and curiosity that transcends generations. These spacecraft, launched in the late 1970s, were designed for a mission that was supposed to last only a few years. Yet they have endured, continuing to send back data from billions of miles away. Their longevity is a testament to human ingenuity and the relentless drive to explore the unknown. The story of Voyager is, in many ways, the story of humanity, a tale of reaching beyond limits, of daring to ask questions that have no easy answers. As we look to the future, the heliopause will remain a key focus of scientific investigation. New missions are already being proposed, including probes designed to study the interstellar medium in detail and to map the heliosphere's boundaries with unprecedented precision. These missions could use advanced propulsion systems, such as solar sails or nuclear electric engines, to reach the heliopause more quickly and gather more comprehensive data. The heliopause also holds potential for international collaboration. Its study is a global endeavor, requiring expertise from physicists, engineers, astronomers, and more. By pooling resources and knowledge, the scientific community can accelerate discoveries and unlock the secrets of this fascinating boundary. Such collaboration could serve as a model for tackling other grand challenges in space exploration, from the search for extraterrestrial life to the quest to understand dark matter and dark energy. The study of the heliopause is not just about answering questions, it's about asking new ones. What happens to the heliosphere as the sun ages and eventually becomes a red giant? How does the heliopause interact with the interstellar medium over geological timescales? Could other stars have similar structures, and if so, how do they differ from our own? These questions push the boundaries of human knowledge, driving us to explore, to experiment, and to imagine. The heliopause is a boundary that invites us to cross it, not physically, perhaps, but intellectually. It is a frontier that challenges our understanding of the universe and our place within it. As we continue to study this enigmatic region, we are not just exploring the edge of the solar system, we are expanding the horizons of what it means to be human. The heliopause's importance extends beyond the confines of our solar system. It offers a gateway to understanding the broader interstellar environment and how other star systems behave. By learning how the Sun interacts with its environment at the heliopause, scientists are unraveling clues about the behavior of other stars and their interactions with the interstellar medium. This is especially significant when considering the discovery of other star systems and exoplanets. For instance, exoplanets orbiting stars with different solar wind profiles might experience drastically different space weather, which could affect their habitability. The lessons learned from studying the heliopause could eventually help scientists develop better models to understand the potential for life beyond Earth. This focus on the heliopause connects to broader research questions about the nature of life in the universe. Could other solar systems have their own heliopause-like structures, offering protection to planets that orbit those distant stars? If we are to find signs of life elsewhere in the galaxy, understanding these outer boundaries is key. If life exists on a planet orbiting a distant star, its proximity to the heliopause-like boundary could offer protection from cosmic radiation, much like Earth's heliosphere does. While the vast distances between us and these distant star systems make such investigations a long-term endeavor, the heliopause gives scientists a model for understanding how stars could shield potential life-bearing planets in the vast stretches of interstellar space. While Voyager continues to explore the heliopause, we can look forward to an even more profound exploration of space in the coming decades. The data already gathered by Voyager is astonishing, but it is just the beginning. As more advanced spacecraft, like the James Webb Space Telescope and others yet to be conceived, are launched, we will gain deeper insights into the space between stars and how our solar system relates to the galaxy. In some ways, the heliopause has become one of the most significant scientific frontiers in space exploration because of the questions it raises. It asks us not only to look outward but to think deeply about what we know about our own solar system and our place in the larger cosmos. The study of this region, and the broader understanding of the heliosphere, may also redefine our understanding of physics. The behavior of particles and magnetic fields in the transition between the solar wind and the interstellar medium pushes the boundaries of plasma physics and space weather. The phenomena observed at the heliopause challenge existing models of magnetic and plasma behaviors, forcing scientists to update their theories and predictions. This process of refinement could ultimately lead to breakthroughs in areas like energy production, particularly in fields such as nuclear fusion, where plasma physics plays a crucial role. Another aspect of the heliopause's intrigue is its potential for revealing new insights into the nature of the universe itself. The boundary where the sun's influence fades into the interstellar medium is also where our understanding of space-time could evolve. Many scientists believe that studying the transition of the solar wind into the vacuum of interstellar space could eventually help explain the nature of the vacuum itself. Could it be that the transition into interstellar space is also a key to understanding dark matter or dark energy? The gap between ordinary matter, like the particles in our solar wind, and the mysterious dark matter that makes up the bulk of the universe is still one of the most significant unknowns in modern physics. The heliopause, with its unique characteristics and position, may hold clues that one day allow us to understand the unseen forces that shape our universe. Beyond these technical and theoretical insights, the heliopause also serves as a profound reminder of the vastness and complexity of the universe. Our solar system is just a speck in the grand cosmic landscape, and the heliopause is a tangible boundary, a point where the sun's grip on its surrounding environment begins to weaken and the star's true freedom in the cosmos is revealed. The sun, our source of light, warmth, and energy, has its own limits. The realization that our familiar cosmic environment has boundaries is humbling and a reminder of the scale of the universe around us. As our understanding of the heliopause and interstellar space evolves, we might begin to look at the sun in a new light. Instead of seeing it simply as a source of light and energy, we will understand it as a part of a much larger system, one that interacts with the rest of the galaxy, contributing to the larger cosmic dance of matter, energy, and forces. The heliopause forces us to question how isolated we really are within our solar system, and whether we are just one small part of a much larger cosmic pattern that we have yet to fully comprehend. Voyager 1, the first spacecraft to reach the outermost boundaries of the heliosphere, carries a golden record that includes sounds and images meant to represent humanity. As the spacecraft continues its journey beyond the heliopause, it becomes a symbol not only of human ingenuity, but of the curiosity that drives exploration. The heliopause, this seemingly invisible boundary, represents the edge of human exploration at the moment, but it also signifies the gateway to the unknown, a place that sparks the imagination of future generations of explorers who will one day venture into this mysterious expanse. And so, as Voyager 1 continues its journey through interstellar space, we are left to ponder the future of space exploration. What lies beyond the heliopause? What mysteries await us in the uncharted territory where the solar wind meets the interstellar medium? The heliopause, as a scientific frontier, represents both the culmination of our current understanding of the solar system and the beginning of a much grander, more profound journey into the cosmos. With each new discovery, we edge closer to understanding not only the nature of our solar system but the very fabric of the universe itself. The heliopause, in all its complexity, remains one of the most profound mysteries of space, a boundary that invites us to explore further and dream bigger. As we continue to explore the heliopause, it's important to remember that this boundary isn't just a physical location that we're able to study and observe. It also represents a turning point in our scientific methods and technological development. In many ways, the data gathered from the Voyager probes marks a historical moment in humanity's ability to explore space. The science behind how we understand the boundary between our solar system and interstellar space has been years, even decades, in the making. The research that will continue from this discovery is something that will shape not just our understanding of our own solar system but will inform how we approach interstellar exploration in the future. Looking at the heliopause, one might wonder why this region is so important for understanding the solar wind and interstellar medium. The reason lies in the intricate interactions that take place between the sun's influence and the cosmic environment surrounding it. For a long time, scientists struggled with understanding the boundary between these two regions. After all, the solar wind does not simply stop abruptly at the heliopause. It gradually diminishes as it travels outward. The influence of the sun's magnetic field also weakens as it stretches further from the sun. This gradual shift provides valuable data to scientists who study how magnetic fields behave on a large scale. It is precisely in this zone of transition, where the solar wind meets the cold, sparse interstellar gas, that we find the greatest opportunity for discovery. The study of the heliopause is also integral to understanding solar storms and how they affect both our planet and interstellar space. The sun constantly releases bursts of charged particles and radiation known as solar winds. These solar storms, while usually harmless on Earth thanks to the protective magnetosphere, can affect satellites, communication systems, and even power grids. The further we venture into space, however, the more vulnerable spacecraft and explorers will be to the effects of solar radiation. Studying how solar storms behave at the heliopause and in interstellar space will give us vital knowledge for protecting future missions beyond Earth's protective magnetosphere. For instance, astronauts embarking on deep space missions, such as missions to Mars or further destinations, will be exposed to these solar winds. Understanding how the heliosphere shields Earth from harmful radiation and the point at which that protection no longer applies is essential for the safety of human exploration. In terms of space missions, the heliopause marks the point at which we can no longer rely on direct observations from Earth-based instruments. While we've been able to monitor the space between the Earth and the outer edges of the solar system using satellites and telescopes, the unique characteristics of the heliopause require instruments that can venture beyond this boundary. As the Voyager probes continue their journeys, they provide us with data from beyond the reach of any other current spacecraft. Their instruments measure plasma density, magnetic fields, cosmic rays, and charged particles, sending back invaluable information that informs everything from future mission planning to our understanding of the interstellar medium. The next logical step in space exploration might very well be the development of new spacecraft specifically designed to study the heliopause up close, and to track the behaviors of solar wind as it begins to dissipate into the greater universe. Such missions would open new doors to the study of distant star systems, as well as the mysterious phenomena that shape the structure of the galaxy. The data from Voyager 1 and Voyager 2 are already invaluable to this mission, but future spacecraft that are capable of taking advantage of more advanced technologies could significantly expand our understanding. There's another fascinating aspect of the heliopause that makes it a central point in our quest for knowledge. It serves as a powerful reminder of just how interconnected the universe is. At the heliopause, we can begin to see the Sun as part of a much larger system. The boundaries of the solar wind are just a small piece in a grander galactic puzzle. The interstellar medium is not a static entity, it is dynamic and ever-changing, driven by countless forces. As the Voyager probes pass beyond the heliopause, they are becoming cosmic messengers, able to send back information about this vast and unknown space. Through their continued exploration, we are learning that the Sun's influence doesn't end at the edges of our solar system. It ripples outward into the greater galactic space. Understanding this interconnectedness between the solar system and the galaxy allows us to recognize the solar system as part of a much larger cosmic ecosystem, where interactions between stars and their environments shape the very structure of the universe. The heliopause has even potential for exploring the future of humanity's place in the universe. As the human race continues to look to the stars, one of the greatest challenges will be the physical limits of space exploration. Voyager's crossing into interstellar space shows us that there is a boundary to what we currently know about space. However, this boundary is also a stepping stone for the future. As humans look toward traveling beyond our solar system, towards places like Proxima Centauri or even further star systems, the experiences of Voyager become a roadmap for those future missions. By studying the heliopause, we gain insight into the challenges and triumphs that await future generations as we push past the confines of our solar system. Even though the distance is staggering, we might one day hope to send human missions beyond the heliopause. If that goal seems far-fetched, it's important to remember that humanity's exploration has always been marked by overcoming seemingly insurmountable challenges. In the same way that the moon landing once seemed impossible, traveling beyond the heliopause could be the next monumental leap in human space exploration. The information we gather from the heliopause will undoubtedly be key in making that leap possible. Moreover, the heliopause challenges us to think about the very nature of space travel itself. As spacecraft venture into the interstellar medium, they must deal with new types of cosmic radiation, extreme temperatures, and other phenomena that don't exist in the inner solar system. The technology and materials used to build spacecraft capable of surviving in such harsh conditions will push the boundaries of engineering and materials science. What we learn from exploring this boundary could ultimately result in breakthroughs that not only enable further space exploration, but also have practical applications here on Earth. For example, advanced materials that could protect spacecraft from radiation may also find uses in other fields, such as medical technology, where radiation protection is critical. As we look forward to the ongoing discoveries at the heliopause and beyond, it's clear that the frontier of space exploration is expanding. Voyager 1's journey is far from over. The spacecraft is expected to continue transmitting data for many years to come, offering valuable insights into the nature of space at the edges of our solar system. Its mission, once thought to be a simple flyby of the outer planets, has now become one of the most groundbreaking space exploration efforts ever undertaken. But the heliopause remains only one part of the grander puzzle of the universe. What's beyond it? What lies in the vast and empty expanse of interstellar space? As we continue to explore these frontiers, the heliopause will be the touchstone that leads us deeper into the unknown, pushing humanity ever forward in our quest to understand the cosmos. As we continue to push further into space, the implications of the heliopause become more significant, not just for scientific discovery but for our philosophical understanding of the universe. The boundary between the solar wind and the interstellar medium, where the sun's influence fades into the greater galaxy, forces us to confront an incredibly profound question. What does it mean for humanity to be on the edge of the solar system? What is the true nature of our place in the universe? This question has philosophical, scientific, and existential implications that continue to shape the way we view our role in the cosmos. The heliopause challenges our perceptions of our solar system's edge. In many ways, we've been trained to think of our solar system as something finite, limited by the orbits of distant planets, objects in the Kuiper belt, and the boundaries of the heliosphere. But when we look at the heliopause, we realize just how much more is out there. We are living in the midst of a much larger universe that is ever expanding, full of unknowns, and continuously challenging our understanding of space. The heliopause, like the vast expanses of space beyond it, forces us to acknowledge that the solar system itself is only a tiny fraction of the larger galactic landscape. Perhaps one of the most thought-provoking aspects of the heliopause is the knowledge that it isn't a fixed boundary. It is a fluid, dynamic region that shifts and changes over time. As the sun's activity fluctuates with the solar cycle, the size and nature of the heliopause change as well. This constant change in the boundary reminds us of the unpredictable and ever-changing nature of space. Understanding this flux is critical for future space missions and for anticipating how our solar system will interact with the interstellar medium in the coming years. These dynamic forces are a constant reminder that space is not static. There is always something new to discover, new patterns to understand, and new challenges to overcome. In a way, the heliopause serves as a symbolic gateway, a reminder that we are constantly reaching for something more, something beyond what we already know. It represents both a physical boundary and a conceptual one, prompting us to ask what lies beyond. As we continue to learn from the data gathered by the Voyager probes, it's important to remember that this is just the beginning of our journey into interstellar space. We've crossed the threshold, but what lies on the other side remains largely unexplored. The discovery of the heliopause has opened the door to an entirely new era of space exploration, one in which we can look beyond the boundaries of our solar system and into the deeper regions of the galaxy. The information we've gathered from Voyager's encounter with the heliopause is groundbreaking, but it's only one piece of the puzzle. The data we continue to receive from the Voyager spacecraft will provide valuable insights into the properties of the interstellar medium, the behavior of cosmic rays, and the magnetic fields that influence our galaxy. But it's likely that we'll need further exploration to fully understand the heliopause's role in shaping the larger structure of the galaxy. In the future, space missions may push far beyond the heliopause, giving us a first-hand look at the properties of the interstellar medium and how it interacts with other star systems. The possibility of future interstellar probes, capable of traveling even further into the galaxy, is not entirely beyond our reach. One of the most exciting prospects of space exploration in the coming decades is the idea of sending a spacecraft to another star system. If missions like these come to fruition, they will not only further our understanding of the heliopause but also provide a much broader context for understanding the role of our solar system within the larger framework of the universe. As we look beyond the heliopause, we also begin to ask the deeper questions about what exists in the vast, unknown reaches of interstellar space. What is the structure of the galaxy beyond our own solar system? How do stars, planets, and other celestial bodies interact in regions of space where the sun's influence no longer reigns supreme? What kinds of forces shape the interstellar medium, and how do these forces shape the behavior of matter in space? While the heliopause is an important boundary to understand, it is only a small part of the larger picture. The answers to these questions are vital for furthering our understanding of the universe and guiding future exploration. In the meantime, the data we gather from the Voyager probes continues to reveal new insights into the behavior of solar wind and cosmic radiation. As Voyager 1 and Voyager 2 move further into the interstellar medium, they will encounter new challenges and phenomena that will provide additional clues about the nature of the universe. The vast distances between these spacecraft and Earth mean that we are witnessing some of the most distant observations in the history of space exploration. Every bit of data that comes back from these missions provides us with a snapshot of the farthest reaches of our solar system and the boundary where our influence as a species begins to fade. But for now, the Voyager probes remain our ambassadors to the stars. As they continue their journeys into the unknown, they are sending back messages from the outer limits of our solar system, messages that will inform the future of space exploration for generations to come. These probes are not just collecting data for scientists. They are charting the future path of humanity's exploration of space. Every bit of information that comes from the Voyager spacecraft brings us one step closer to understanding the broader universe around us. We are learning about the heliopause, the limits of the solar system, and the transition from our familiar surroundings into the mysterious expanse of interstellar space. In the end, the study of the heliopause is much more than a scientific endeavor. It's a journey of exploration, discovery, and ultimately, of human curiosity. The heliopause represents the edge of our solar system, but it also symbolizes humanity's constant drive to push beyond the boundaries of what we know, to seek out new knowledge, and to explore the unknown. Whether we are studying the solar wind, cosmic radiation, or the vastness of the interstellar medium, the heliopause reminds us that the universe is far bigger and more complex than we can ever truly comprehend. But that won't stop us from trying to understand it, one step at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.